good morning and welcome to the stream. We should start in about 30 minutes, so hold on. Grab your coffee or something and come back. See you then.
You've been out far too much lately. I have to stay home tonight. She's in love with him. Very much.
Hello and welcome to HITB Lockdown002. We should be starting in about 2 minutes. Good morning, good afternoon, and good evening to all attendees wherever you are. Welcome to the second edition of HITB Lockdown series. Despite the current circumstances, we will try our best to provide you with our usual HITB conference vibe and activities. With that said, we have an interesting lineup of talks running throughout almost today and tomorrow. We also have our command and control challenge, villages and labs. Thank you to everyone, all of you who continue to support us as we continue to figure out this evolving year. We will try our best to give you our usual true HITB vibe and headache-inducing content in the next 2 conference days. We have a great lineup of 30 talks that will run across today and tomorrow for a total of 65 hours of content. Before we start, Dylan, lead dog, would like to all introduce you personally.
Good morning, guys, and welcome to the second live stream. So I was really hoping that we'll be in Singapore at this point in time, chilling and actually having a conference in person. But unfortunately, as it's very clear, the COVID situation is still ongoing, and most international borders are still closed. But nevertheless, in true hacker spirit, we continue to think up of ways to keep ourselves busy and make the best of the situation, and of course to keep you guys entertained as well. And so what do we have lined up for you guys in this lockdown, right? This time's HITB Lockdown002. We've actually added quite a lot of stuff since the last time that we did this in Amsterdam. Firstly, like the Amsterdam conference as well, this lockdown edition will feature all of the speakers that were supposed to have been at the Singapore conference. This also includes the keynote speakers, so a big thanks to all of these guys for taking the time and energy to put their talks together, despite being super busy and obviously having their own commitments to see to. And obviously they're not also in Singapore to enjoy some awesome weather and some great food with us, right? So yeah, big up guys. Really, really appreciate the effort that you guys have taken. With that, we've also actually added more content to the lockdown edition. The last time we did a single track, like one single stream. And this time we've doubled it. We're actually going to be starting this particular track 1 is starting now at the Singapore time zone of 10 a.m. And then we'll have track 2 that will start following the EU time zone And this essentially means that for those of you in Asia, you're going to have about 12 hours worth of content per day that you can watch and enjoy. We've also added more labs, right? So these are hands-on interactive sessions where you can actually try out stuff and play around with things. And these labs are actually separate from the YouTube stream, so what you're watching right now. We've arranged for them to actually happen on Zoom. So we've got 3 labs planned. There's going to be one on car hacking. So if you're interested in automobile security and CAN bus stuff, you should join that. There's also going to be a lab on software-defined radios. And then we've got a special lab for you guys on the chilling framework. They're going to be covering on how to build a fuzzer using their framework, right? And this session in particular proved to be so popular because when we announced it, we thought, we don't really need to have a registration for it. People can just show up. It should be fine, right? Well, it seems that a lot of you are really, really interested in the chilling framework. So, in the interest of not having it go crazy, we decided to split it into 2 sessions. So there'll be one chilling lab that's running today. And there'll be another similar session, same topics that was covered today, happening tomorrow as well. So if you haven't signed up, go and take a look at the registration form. I think there's still a couple of seats left. So yeah, go and check out those labs that are happening. We've also added more contests and more games. There's no traditional Hack in the Box team-based CTF happening. But we do have a car hacking CTF. So you can, go for the car hacking lab, learn about CAN bus stuff, and then try your hand at the CTF. There's also a web and application focused contest. It's called Command and Control, and it's being run by the guys from Security Innovation. And then we've got a crypto challenge, like a special crypto challenge by the guys from Zenith Labs. So both the Security Innovations challenge as well as the crypto challenge have cash prizes that's being offered. So if you're not watching talks or you get bored of watching talks, go and try your hand at one of those contests. And then last but not least, we've actually added our own Discord server. So if you want to come and chat with us, or you have a question for speakers, or you want to just hang out with other conference attendees or live stream attendees, hop on to Discord. So if you're on our website, you'll just see there's a little link that says HITB Discord. And you can also participate in the lab discussions. It's also going to be happening on the Discord server as well. I think that's pretty much it for me for now, guys. I'll come back again and speak to you guys tomorrow evening to wrap up. And I'll also tell you guys a little bit about what we are hopefully planning for the rest of this so far quite chaotic year. In the meantime, grab your drinks, grab your snacks, get comfortable, enjoy the stream. I'll see you guys on Discord, man. Lead dog out.
Hey everyone, and my name is Alex Matrosov, and I'm glad to be today here to present my keynote, Hardware Security is Hard, How Hardware Boundaries Define Platform Security. And actually, today we have these difficult times, a lot of conferences get canceled, I'm glad Hack in the Box in Singapore actually have online event, and we, all of us, get opportunity to enjoy this awesome conference. So also this COVID-19 situation create a lot of interesting circumstances for security, and we will cover some of the topics today too. Few words about me. Actually, I'm leading offensive security research at NVIDIA, and previously I've been a security researcher at the companies like Cylance, Intel Corporation, and ESET. So I'm doing security research since 1997, focused on reverse engineering, hardware security, embedded firmware devices, exploitation, and a lot of other interesting stuff, include automotive. Think about, we actually have really a lot of changes in modern attack surfaces, and security industry visibility point actually just a really like visible part of the iceberg, but we have a lot of modern persistence techniques which is tied to the hardware and firmware, and it's keep invisible for any endpoint solutions, and actually we don't have any automated tools and approaches for finding hardware and firmware implants, and actually it's creating a lot of differences in our modern attack surfaces and threat modeling approaches. I've been talking about advanced threat evolution last year and about researchers' arm race, where actually I've been focused at how the persistent threats get evolved and how the firmware currently playing the key for the differences of the persistent threats in nowadays. You can find this presentation by the link on this slide. But let's back to our main topic of the keynote, how security boundaries actually define the platform security. And think about hardware threat model really separated from the firmware threat model, but each chip on the device has their own firmware. And the problem is we really not define the threat modeling across the different devices on the board together. We're really separating it for each chip, individual chip, which is basically a mistake, because nowadays it's hard to spot real boundaries between different hardware and firmwares because it's communicating. And actually, if you get attack one chip, you can cross security boundaries, which will be making much more easier attacking other chips after that. It's why we should define the hardware threat model and firmware threat model together and not separating it. And actually, we need to look on the whole platform to define the right threat modeling. But actually, it is hard because we do have a lot of third-party components which is vendor not have access to, and it's just trust their OEMs, which is ship these chips and actually provide the firmware binaries to the platform developer. And it's created a lot of interesting spots in the threat modeling process. But let's back how usually security architects define threat modeling. And actually, look on it. This brilliant piece of the slide being captured from the UEFI forum presentation, and actually it says the analyzing security requirements and platform diagrams, it is enough to basically understand the threats and define the threat model. But in my opinion, really, if we just look on the diagrams and security requirements, it says nothing about threats. It just says a lot about what kind of firmwares and hardware components we'll be using on this device, but not really about the threat modeling, because you look on the requirements, you don't understand what kind of the firmware version, what really the chip does, what is version of the Bluetooth stack, or what kind of USB microcontroller we'll be using there. Even sometimes on the requirements, it's not defined particular OEM, and it's create a lot of blind spots on the threat modeling process. And it's hard to find real security problems in the platform diagrams, right? So based only on requirements. And if you look on the National Vulnerability Database, it is really numbers of vulnerabilities related to the firmware significantly increasing every year. So basically, we have already almost the same number of vulnerabilities reported by researchers and third parties to the certs from the vendors or US cert, which has been reported last year. So it's almost doubled already by the numbers being known from the last year. So basically, what's happening, a lot of vendors, it's the same actually presentation from UEFI forum, and a lot of vendors actually looking on the firmware through obscurity prism. What that means, if the security through obscurity works, the firmware binaries is actually available for everybody. Let's keep it private, and researchers will be gone. Nobody will be found the vulnerabilities. And this model actually doesn't work at all, because researchers can extract the firmware from the device, researchers can find leaked firmware versions in the internet, and a lot of other ways how it can be firmware get to the researcher hands. And if it's only the way for create the boundary, it is actually very bad practice. And I'm glad not a lot of vendors follow that way. And I really believe we should have access not the binaries, but technology specs also should be transparent to create the good transparency level for the other vendors who creating the hardware. Because think about modern clouds have this foundation based on the hardware, and if it will be no information about the hardware design, how we can trust this hardware? It's really hard. I was talking a bit about the persistent threats in my book, but today it's not about that. So I really like this picture, which is basically shows the Kraken try to attack this guy in the bot. And I would say it is kind of like a joke about security architect, because security architects not really understand what the persistent threats and hardware or firmware plans means, and usually they do a lot of mistakes on the threat modeling about this kind of threats. As example, hardware and firmware security, it's not the same as a summary of all the boundaries across the board. As I mentioned before, we really try to separate security boundaries for each device on the system board, which is a huge mistake, because we actually really make a threat model focused on TPM, PMU, or base management controller, or embedded controller, or GPU. And it is really separating different devices. But think about if one of these devices can be malicious, it's crossing the boundaries, and it will be equal boundaries for other devices in many cases, which will be basically create a lot of more opportunities for the attacker. What does that mean about the hardware security boundaries? Most of these chips are not under direct control from the hardware vendors. And it is really like third-party contracts, and vendor doesn't control the hardware and firmware, and even more, how you can create the threat model if this chip, it's not yours, right? So the threat model also need to be include the time of patching the vulnerabilities on the third-party chips and the firmwares, right? And it makes this process very complicated. Also, it is a lot of things connected to UEFI firmware BIOS, right? And also consider it to generate the trusted input-output interfaces, but mostly of the supervision scope of the main CPU, right? How we can trust anything that is under, not under our control. In current realities, hardware and firmware threat modeling shouldn't be undivided. Because we have a lot of ways how we, as example, can develop secure boot, right? And in many cases, secure boot will be, root of trust for secure boot will be TPM. In current trend model, hardware consider it trusted in many cases. As example, we just think our TPM is not compromised, right? And was brilliant research from Jeremy Boone about TPM interposer, and Tremel Hudson actually did pretty, not the same, different way, but also interposing TPM signals over soldering on the chip direct wires. And you can see this on the picture. And a lot of server boards actually have the separate TPM, which is just connected on the slot, and you can see it on the left side of the slide, which is also hard to consider trusted root of trust, right? But let's back to base management controller. So we just seen this picture where a lot of different components on the system devices exist, right? And base management controller, it is inside the trusted boundaries, actually. And what that mean? Base management controller, it is kind of like a remote interface for the system management board, because think about across the data centers, it is thousands of the devices, right? You can't go and physically reboot each machine or update each machine. So what that mean? Base management controller can update the system firmware. It can remotely reboot the machine, or even more, it can actually provide some debugging interfaces. And UEFI firmware actually blindly trusts most of the hardware because it is not under control, and how you actually can check it is a real device which has been originally installed by the vendor of this system platform and not faked by malicious attacker. But the hardware can attack UEFI firmware, and actually in many cases even more firmwares across the board. So it was very good research by Alexandre Gazette and Geoffrey Cherney on Zero Nights 2018. I really recommend you, if you're not seen yet, to look on it about their very interesting attack on Hewlett-Packard ILO BMC. But how many third-party chips in your platform? And actually it is a lot, because we have a TPM, USB controllers, embedded controllers, fingerprint devices, touchpads, and many, many others. And all these devices has the firmwares. That's mean the firmwares can be updatable or not updatable. As example, your touchpad in many cases not authenticate the firmware. So basically, of course, it's not a lot of things you could do from the touchpad, but think about if it will be something more powerful. And we will be getting some places where common mistakes can provide really interesting opportunities for the attacker. Let's back on BMC. So BMC actually can update the firmwares for most of the devices across the board. So basically, even more, it can update the TPM and have an infinite control under SPI flash controller. It is have a separate network interface, not dependent on the system board interface provided for operating system and others. It's just separated for functional purposes. Also, in many cases, BMC has a DMA access, which can actually create additional ways for the attacker. And it's exactly been covered by Alexander Gazette and Geoffrey Charney on the research from the previous slide. But if you think about what will be if BMC can provide a remote interface for the debugging of the system board. And it is actually can be, because I just recently found on the American Megatrends documentation, they do have actually American Megatrends hardware debugger implemented in the BMC firmware interface and actually communicates over the network to perform host debugging operation. And actually, if you control BMC in this case, you can get even more privileges to attack very sensitive information and actually screwed up most of the security technologies across the board. And if you think debugging on Intel platforms, it's very expensive. Yes, it's been before Positive Technologies researchers not release their research about how you can create your own debug cable for $20, and it is actually make much more cheaper, because original Intel device being sold under NDA and being cost about $2,000, but it was not really a price for that, right? Also, interesting thing, when we have a deal with counterfeit devices with the hardware implants. And it is actually not rare situation where we can see this kind of devices used show up in the market, right? So, and it was recently F-Secure found Cisco devices, which has additional GTAC pins on the board, and it was possible to basically get full access over these pins to the Cisco router without having original credentials. Also, of course, you remember Supermicro case, right? And it is actually very interesting. We get much more attention after this Bloomberg presentation to the hardware implants. And I would say Bloomberg make very interesting thing to wake up the world to pay attention more on this kind of threats. But let's think about what happens in the cloud. We have this cloud ecosystems, which is powered by software infrastructure, and data center hardware provides the foundation for that, right? But we have the root of trust, which is inside the silicon. And what if something will be get wrong, right? So how usually we have root of trust separated from original system board. So in many cases, it gets implemented on FPGA, which is actually third-party chip, and or others third-party chips, which is basically provide some generic APIs and their own root of trust, which is not under control of the vendor. So basically, it's not changed much because we still have the third-party chip on the board, which is provide root of trust. But in this case, actually, Microsoft create Project Cerberus, which is being created for create this kind of a transparency for supply chain and actually attestation for the platform. Same thing, actually, Google been creating with Project Titan. At NVIDIA, we have a Falcon chip, which is also hardware root of trust for NVIDIA products. So it is actually very important for the modern cloud providers to have their own transparency and visibility across the device. Because if you have a third-party software and hardware control root of trust, it's really hard to validate it and understand it was not modified with any additional functionality or malicious code. I remember the case from previous year presentation when Alex Gazer was kind of a part of root of trust for security technology created by Intel. So how the update process for embedded controller works. We have an update tool which is based on generic Lenovo TDK update tool. Embedded controller update image actually mapped to the memory, and we set particular Lenovo EC firmware update in VRAM. After that, actually, after NVRAM variable is set, firmware start update process on their side. Basically, firmware loads the firmware image on the firmware memory and start validate the firmware header, and after that update EC firmware. If you look on this code, it is obvious race condition, time to use, time to check attack, right? So basically, if you look on T540p case, even more, it is just update embedded controller with unsigned binary. What that means, even if the binary been signed by Lenovo, this models doesn't check any signatures. So you can modify any embedded controller binary and just flash it. But actually embedded controller, it's quite powerful in many cases device. It powered in actually with ARC or ARM chips, and it can in some cases have a DMA access tool and actually connected to LPC bus, which is also can be some way for the attacker to screw up the hardware. Think about, we have a lot of vendors involved on the firmware development nowadays. I'm talking about UEFI system firmware, and if you think about reference implementations, as example, can created by Intel, AMD, and then we have independent BIOS vendors like a Phoenix, Insight, or American Megatrends. Also, device manufacturers get involved because they basically develop the system boards And original equipment manufacturers like Dell, Lenovo, Hewlett-Packard, and Apple have some additional code created just for their devices. And if you think about Dell, Lenovo, and HP, actually modifications came after device manufacturers. It is really small. It is kind of like about 10-15% of the whole code base. And it's not making huge differences because most of the code being provided by American megatrends at Intel with a reference code for the technologies across the system board and new CPU features. If you think about how hard it is reverse engineer more than actually divided between this silicon-based level bootloader and some other stuff, and that means it is a silicon issue which is hard to patch in the field. So how we can reduce the silicon level risks and attacks? The Google did Open Titan project, which is actually open a lot of information and specification in the code regarding Titan chip silicon. So Open Titan actually have much more visibility because you can check much more layers, not only the firmware, regarding how RTL is implemented on this chip, right? But also, anyway, we have some IPs from third parties, which is still is blind spot. And chip fabrication and production, it is also based on the third-party fabs, right? But anyway, it's created huge differences between traditional root of trust chips. And it's why cloud providers try to gain this transparency for them. But anyway, because the Titan chip in many cases is unpatchable, let's remember this vulnerability found in the Bluetooth last year, and Google recalled the Titan security keys because this vulnerability is based on silicon. But silicon patches in many cases is impossible, so it's make very expensive way to patch, basically to change the device to your customers. So, but let's talk about how modern industry standard bootloaders works. We have a small ROM, which is actually pass the control under the loader and second stage loader. And usually root of trust in these chips tied to the ROM, and ROM is unpatchable. So basically, if we have vulnerability inside the ROM, or somebody from GTAC can basically bypass the ROM validation for the loader, so it's done. And in this case, I would say it is a dangerous place because if this code not formally verified and still written on C, it's kind of difficult to believe it was no issues there, right? And also the complexity for the support, as example, if the device breaks, we need to understand what happens and actually make a recover. So usually this kind of ROM can unlock serial, UART, or GTAC, and it's create additional attack surfaces. So secure boot fix everything, right, in this case, but it is not really true. So think about, we have this stage 0 boot ROM, verifies, loads, and executes stage 1. stage n, and stage n+1. So basically, if any of these layers have their own vulnerability, but we exploit this vulnerability after validation the level, the root of trust basically transfer it to this stage after that. And attacking it, we basically know we have a full control on the boot process, which is create kind of problematic, and modern secure boots is really complex because of that. Silicon bugs stay forever with the customers, and we need to remember that, because basically checkmate vulnerability create a huge issue where we have more new devices affected by this vulnerability. So what happens, this boot ROM issue inside the silicon, and because we have already devices in the field, all these devices is unpatchable. And because of that, it's still, we can read a lot of research based on this issue. Another good example, it's Intel CSME issue from 2018, which is basically initialize page directory, turns on paging, and maps ROM for CSME. It's small piece of the code, which is immutable and basically unpatchable in case of the issues. What happens, IOMMU DMA protection turn it on too late, and attacker can have opportunity to remap execution pages to arbitrary physical address, as example to spy flash. That's it, right? So, and these devices in the field, it's a lot of devices still unpatched. Security dongle, I would not name the company, but they really say we have a top grade security for our dongles and can save your private keys. But this chip was not created and certified for the critical security places. That's mean we can find a lot of weird stuff about this chip. And basically, this diagram on the right side shows how IS key can be leaked over the power side channel analysis. And also, this particular chip is locking JTAG over set up the pin during the boot. So very interesting chip to be a security used in the security dongle, right? It's why I say we have a lot of different problems across different devices, which is create hardware security, make it secure, hardware security hard. And we need to understand the full picture on your threat model and security requirements. It's not enough. We actually, security requirements, it is just the first step which you think about your level of security. So you create the security requirements, you create the threat model, but after that, offensive security team in your company should go over and understand the reality of your threat modeling. I would say internal pen testing with offensive security researchers on your device created by your company, it is really where the threat modeling meets a reality. Because in many cases, the requirements can miss something. The threat modeling on the early stages, it's very different when we actually understand or get the first silicon. So I would say modern threat modeling process, it's very difficult, and it should be involved many people from the company which is building and working on this project related to the device, whatever. And without this, it's actually make it very hard to make it secure. we really need to rethink the meaning of hardware security and realities of the modern threat landscape, because the threat landscape is changing really fast. But our understanding about the threat model really sometimes it's just freezing for the years, and we try to think about the attacks which is already not very relevant, and we don't have the visibility about new attacks which actually modern attackers can use. It's why offensive security research team, it's very important to gain this visibility and create productive collaboration between the product teams and offensive security research to develop the secure products for your customers. Thank you very much for your attention, and I will be happy to answer all the questions.
Hi guys, I'm sorry we're having a bit of a troubleshooting issue at the moment. We should get things running up and smooth once again after this. Alex will be on a call slightly. Just give us a few minutes to fix this problem. Again, we apologize for the confusion. Hello all, welcome back. We are truly sorry about the issues we had just now. It was due to some network issues, but we're trying to get that fixed so that it does not affect your experience moving forward. Again, truly sorry about that, and do bear with us. Due to that, we were not able to give Alex a Q&A live session. If you had any questions, could you please put that in the Discord channel, and we will make sure to get that to Alex, and he would be replying there. Up next, we have Jiang SHANG-DE. He is a researcher at SciCarrier who currently focuses on research about incident response and endpoint security. His talk is titled The Dojo of Blue, How Adversary Emulation Can Enhance Blue Team Performance. This would be a pre-recorded video, and he would be answering your questions live on Discord and not live on a Q&A session. So if you do have any questions, post it on the Discord channel and he would answer you in real time. Thank you. Have fun.
Before I start this presentation, I want to thank everyone who joined this event, and I am Jiang. I'm a cybersecurity researcher at SciCraft. So today my presentation is about the Dojo of Blue, how adversary emulation can enhance blue team performance. So let me quickly introduce myself. So I am researcher at the SciCraft and speak of the HITB and this year Black Hat USA. And also I'm the UCCU Hacker co-founder. UCCU Hacker is a private cybersecurity group in Taiwan. And my company is our SciCraft. SciCraft is a AI company, so we use an AI solution to solve the security problem. So we have the investigation platform and the threat hunting sensor and the CTI platform. So these are three of our major products. And today, the reason I want to introduce this presentation is because when last year we joined the MITRE ATT and CK evaluation, and today the presentation is about adversary emulation, because we use adversary emulation to practice before we join the evaluation. So before we read into the agenda, and I want to mention the maturity level about how we do the self-assessment in privacy. So in the first stage, we will use the vulnerability scanner to do the vulnerability management to see what possible vulnerability in our endpoint. And we move on to the next level, to the penetration testing. And we do a penetration testing, but only for the external things or some major internal server. And we move forward to we build the internal rating or do the blind rating. We invite the external team to attack to our organization environment. And for now, most organizations are moving forward to the impersonal or continuously reporting, like binding the blue team and the red team together to make them working perfectly. So why we are doing the adversary emulation? Actually, the adversary emulation you can do in the penetration team, rating, or reporting. But the most important part is about tracking the detection and the investigation capability. How can you detect this privacy threat? Can our product detect a known threat happen in the other organization or in my organization history? And after you identify, do you can detect this attack? Then you can see do we need to add more detection about this attack, or we can move forward to other attack. And also you can use adversary emulation to validate your SOC team or your blue team to check them still awake. If after the adversary emulation finish, but the booting didn't arrest anything. You can adjust then the strategy, or do you missing some product so you cannot detect it. So this is the reason we want to do the adversary emulation. And today we will introduce our adversary emulator. So the adversary emulator is different with other adversary emulator. Our goal is first, most important thing is easy to build the environment, and we want to continuously to add the new framework. Because we are security vendor, there's every month, every quarter, there's a lot of our new attack framework coming. So we want to do this. We wanted to design a easy and can maintain the API interface. We can add more attack framework to our testing case. And we also want to training our analysts to enhance their investigation skill. And also, it's the most important thing is make historical security event can be replayed. It's the most important thing where we have we have monitor a lot of customer, and we notice a lot of ATP group. So we want to can replay the attack and the training our analysts. Now, okay, this is today my session agenda. So I will introduce our attack emulator architecture. So I will introduce how we design and what module we have. And the second one, I will introduce about adversary emulation, how we design the process and how our process work. And the third one, I will introduce what attack framework we integrate. And the final part, I will introduce how this whole process to impair and enhance the booting performance and the operation. So this is our architecture quick overview. So we have a virtualization. So the virtualization can tell the rating and booting to know what happened about this time emulation. And then the management console can tell the attack module and the infrastructure builder to tell the infrastructure builder first to build out the environment, and tell the attack module to execute a specific command. And we also have the CLI console. The CLI console can directly interact with the attack module. So we can, if the rating want to add the new attack, so they can use the CLI module to directly execute the command. So I want to introduce the infrastructure builder first. So we use the Docker and the Frigo. For the Docker, we use the Docker for our server console. So our virtualization, syslog, and the management use the Docker. And why we need syslog? Because once we execute the attack command, we will send some IOC or the TTP information to a syslog server, and our management console receive the one task. So it will tell the infrastructure builder to build out the FIDLing infrastructure topology. We will auto create the networking and the endpoint information, and the infrastructure builder will use our Frigo API to execute. And the management will tell the playbook builder to get ready, set out the rating environment like a C2 communication channel and a C2 server communication. And the final, the attack module will execute, and the Frigo API will execute the agent inside the virtual machine and execute the initial backdoor. And this is the image is on the screen is our API design. As you can see, we have a management console just like a previously said, and there's an environment and there's a submodule called endpoint. The endpoints can tell us the status and some simple setting about the endpoint. And we also have attack and the playbook. Like they are separate, but they are working close together, because attack just for we integrate attack module framework. So the playbook is about the story, about how the attack working, about on the FIDLing A they execute some command first and then later move on to a FIDLing B, something like this. So the playbook is about story. And the right hand side is our procedural code about how we work. So we can use the infrastructure builder to build out the Windows 10 or Windows Server and auto create the machine and add the network topology. And we can see what playbook we can choose and use the playbook we choose and automatic start the attack. And because if we want to start build out adversary emulation, you must have the environment first. But build out your own environment takes a lot of time to select the endpoint, backend, and build out the image, OS image, something like this. And so there's two great projects you can reference is a model lab and the attack range. So because this can save your time to build out the OS image, so you can use reference this project. And this is our attack simulator last year. So this is our first version. So the first version in our adversary emulation, you can see there's a visualization about what happened in this APT operation and the attack. Later move on to a FIDLing A and later move to a FIDLing B. Something like this, and the right hand side is what command has been executed when the attack do the adversary emulation. And in this year, we make a big change of our server virtualization console. So our virtualization console changed to the this is still the same. Has a attacker to later move on to which endpoint and how they export, how they later move on. And the right hand side is command execute. But that's the most important thing is about the timeline. The timeline tells the blue team what happened about for example, that the command execute, that user command has been executed like 7 p.m. and what happened before this command and what happened after this command. So we can use a time. The blue team can see this virtualization console to know what happened before the event happened or after. So after we introduce our adversary emulator architecture, so I want to introduce how we design the whole process and how we design the attack playbook. So in this screenshot, you can see we have the attack module and the playbook. So the attack module has supported multiple playbook. So what inside the playbook? The playbook is our storyline. So the storyline has some information about what the environment they need and what attack command they want to execute, and this will really reference to the attack module. And the attack module will execute a real command for the playbook. They say they want to execute the bypass UAC in the Metasploit, so the attack module will really execute the attack command. So the playbook is about the story, so we can support the multiple playbook, so we can attack the multiple playbook in the one time, so this can increase when the blue team start investigation. And how this is our playbook design concept is about because there's a lot of we call the adversary emulator or some TTP testing. But that's not enough for us, because we think the TTP testing just a basic part. We must test the TTP, but we also want our playbook can has a modularized attack produce, and we want the story, because we are not just detect that, we must let booting to understand what happened the attack. So the story is very important to us, and the story can enhance the booting to enhance the booting investigation skill. So we are not just detect the technique, so we also want to enhance the investigation skill. So this our currently we have the 3 playbook. So the first 2 you might familiar with this. We based on the Miter 18CK evaluation. So we create the APT3 and the APT29 playbook. And we also create another our customized playbook we call Dogasa. And this is our Dogasa playbook scenario. So we have totally in a FIDLing environment, we have 3 desktop. And this is 3 desktop, and right hand side is some build-out environment information. And we have a Linux machine and the Windows machine, because we want to see how the booting and how the booting investigation about cross endpoint and the cross OS. Because there's a Linux and Windows machine, how the Linux machine later move into the Windows, and how the booting can detect and investigation this. So these are this Dogasa playbook step. So this first part is our booting need to build out the environment and deploy the security software. And the rating will start attack the user web exploit to attack the FIDLing A, and the FIDLing A to use the SSH key for persistence, and install kernel rootkit to the FIDLing A, and create a tunnel to the internal networking, and later move on to internal web server, and finally later move on to our last endpoint to get some information that we want. And after the rating finish attack, we also call adversary emulator. We finish the attack. The booting will show how when the attack happened, what they detect, and what they investigate when after this attack. I want to break down our playbook Dogasa, the attack produce. So we will in the first initial access we will use a web exploit, EL Finder. So EL Finder is a famous famous file manager for web. So it has many third-party integrate like Django, Drupal, Laravel. So it's very wide in public use. And we use the CV is a command injection vulnerability for the EI Finder. So it's a remote command execute, and it's very easy to launch an attack using a Metasploit. So we choose them to the Dogasa playbook initial access point. So our rating will doing the web exploit and address his privilege through a CH rootkit. It's also known as non-exploit. So the threat actor can use this exploit to invoke to get the root access, root privilege. So it will generate and put our reverse shell in a template update, and compared to the kernel rootkit, It's a kind of privilege calculation and more stable and more easy. And after we do the privilege calculation, the rating will doing the SSH position key. So it's drop the threader will drop their own SSH key, so they can easy to move back to this victim machine anytime and use a SSH. Even they patch the web exploit, they still has a SSH permission. And after they do the positions, and the rating will install a rootkey. So it's hiding their backdoor and prevent the detection. So in this scenario, we use a retail rootkey. It's a kernel mode rootkey and the most famous. And if you find in GitHub, you can see a most start of the GitHub project. And after the thread install rootkey, they want to do the network tunnel and use the network tunnel to reach the internal surface. So in this playbook and in this environment, we set our internal web service, and the thread editor can use the first endpoint to do a network tunnel and get access to an internal service. So while many IT put a lot of defense on the external networking, but the inside network maybe is still vulnerable. So in this use case, we use SOCAT for tunneling, but it's not really malware. So possibly if your Linux server install antivirus, but maybe you still will not detect this one. And then we move forward. We initial access the internal web server, and we also use a web exploit and deploy the malware to the Windows server. And we get into internal web server, and we will do a privilege escalation from IIS system service privilege to a system. So in this case, we use a juicy potato, which we call MAT. The CV number is we use a juicy potato, and we use because it is by the Windows system architecture design, so it's expect the Windows Server 2019. Other Windows Server platforms still has this vulnerability. Can let the other user account to do the privilege escalation. And meanwhile, after we get the system permission, so then we can use Mimikatz to do the credential dumping and get some credential, and then we can do a later movement to the FIDLing C. So in this final step, we later move on to a FIDLing C. We can use a credential from the previously. We can use a BitAdmin, PSQ, WNI to do. We have a lot of options can do later movement, and we will use some tool to do to get some information we want to do a recon, and we will collect some information from the FIDLing A, B, C, and use a Windows MacCap to compression the data we want and send out to the attack machine. This whole step are in our playbook Gaza. So the whole environment is from the Linux machine to the Windows machine, and do the data exploration, and also use a network tunneling. So this is a classical APT case study. So we symbolize the real case and do this playbook. Okay, let's move forward to the attack toolkit integrate. So in this part, I will introduce what post-penetration framework we integrate and why we chose them, the pros and cons, and we repurpose the APT malware and why we choose them, and what the APT group malware we choose. And the first framework we integrate is Metasploit. So we integrate Metasploit. I think most people has familiar with this. The pros is Metasploit has a great community resource. Always has a great latest exploit and vulnerability scan, and the Metasploit has a well-designed session management, so we can easy to integrate. And the last cons is when we try to developing the wrapper of Metasploit, we notice we need to interact with the Metasploit RPC server. It's quite complicated when we trying to interact with this. On the right hand side is our sample code about we modularize the silent cleanup bypass UAC for the Metasploit. So you can see we parameter the session and the local port. Because this attack is quite easy, so we don't have too much thing we need to modularize. And we will, after we execute the attack, we will check do we receive the new agent, new session from this attack. So we modularize every Metasploit attack we want to use. So it's one of the sample. And the second is the second framework we integrate is the Empire. So why we integrate with the Empire? Because we want to demonstration the fireless attack. So previous Metasploit has a traditional penetration framework, but Metasploit has a fireless, but not pure fireless. So we use a Empire. And the Empire has a very simple agent management design, so we can do our own agent management. But there's a concept about because starting last year, I remember the Empire stopped maintaining and the developing. But there's a lot of success. If you want to do integrate the fireless post penetration framework, you can choose other project. And we repurpose the APT malware. So why we want to repurpose the APT malware is because we are security defender. We want to closer the real world case. And so we choose the most APT attack APT group in the Taiwan. So in this repurpose malware, we choose the APT group Water Bear. And because we research and we found a lot of APT malware in our customer, and we reverse a lot. So we found that APT malware usually has a well designed to after security product. So we want to make sure every time we doing this, we can find the APT malware. So the APT malware we repurpose is we call the DBG print. So the DBG print is coming from the APT group Water Bear. Maybe you familiar with is the name aka is Bleed or the Bad Tech. The DBG print is starting from since 2009, and there's a lot of version about the DBG printer. Like the talking security product by inject the shellcode to evidence the security product detection. And also the runtime decrypt and decrypt the encryptor function. So only when DBG will decrypt the function, encrypt function when they are used. So only one function will be decrypted when you do the memory process. And they use a lot about anti-memory forensic. So the DBG DBG print is the most major function is a remote download DLL and load and execute in the memory. So this is a DBG print stager flow. So the first thing, DBG print will check the debug environment and then relocate the function table. And locate the function table and initialize API from the hashed function table and get the DLL. So there's two options when they are using. First option is remote download the DLL from the C2 server. And the second one is the load from the local file. It depends the different operator, they will use a different option. And the final part is get the DLL and decrypt the DLL file and inject and execute in the memory. So the last part is we replace our integrate tool key like previous Metasploit and the Empire. We replace this one and drop our payload here. So after we introduce about what attack framework we integrate, so I will want to introduce about the blueprint part, because previously we say it's about how the adversary emulator, just like most of the EDR product. The EDR product will monitor the system API call. So the PowerShell will call the .NET library, and if you can hook the all API call, then you can know every process include PowerShell, what they are doing in this process. So you can know for example, the PowerShell mimicuts. The mimicuts will load, when they dump credential, mimicuts will load the OSL SAS executable process memory. So it will load the memory to the LSAS, so it's a suspicious behavior, so you can create a detection based on this. So you can find the maximum PowerShell has access to other LSAS process memory. But just like we say, doing this detection are very costly because you want to monitor every API and do a customized detection. And the next level is AMSI, Microsoft Anti-Malware Scanning Interface. So the anti-malware scanning has many functions. So one of the functions is scan every value for the organization. Maybe in some organization, their rating is still fighting with their blue team. They didn't work together. So if we do an adversary emulation, the rating and blue team will working closer, so they can have opportunity to make a good communication with the blue team. And for the blue team, the key benefit is about continuously to developing and validate their detection. This is the most important part for if you run the own threat hunting team or your own security team. This is a very important part. And you also can handle the known threat. You must handle the known threat in your organization history, or some other organization. This is an old trick. But if you the old trick, you cannot handle it, or you cannot detect it, or you cannot investigate it. How you can deal with an unknown threat? And you can also identify, just like we previously say, the data source. So you can identify what data source you are missing. And you also empower your if the blue team has a new member, you can use our adversary emulator, something that designed like this, the playbook, to training them how do they do the real investigation, and they skill up their investigation skill. So above my presentation, and thank you for your time and your listening.
Thank you, Shang. As the speaker will be taking Q&A in the Discord channel, please divert your attention there. He will take questions and answer it there. Our next talk will start in 15 minutes. We'll see you then. Thank you. Hello. Hope you guys are still with us. Starting in about 4 minutes, we have Breakout Scripts of the Westworld by Tang Tianwen and Xiao. So just hold on there and we'll start shortly. Hello and welcome back. Next up, we have Breakout Scripts of the Westworld by Tang Tianwen and Xiao. Tang Tianwen, who goes by the nickname of Victor V, is a security researcher at the 360 Vulcan team, specializing in virtualization security research for the past 3 years, and has discovered multiple critical security vulnerabilities in QEMU, VMware Workstation, vSphere, and Hyper-V. He also discovered the escape of the workstation several times. Xiao is a security researcher at 360 Vulcan team as well, specializing in virtualization security and web browser security. He won challenges for workstation escape on Pwn2Own in 2017. He's also discovered multiple escapes of VirtualBox during the Tianfu Cup in 2018. He's also won the challenge for ESXi escape and QEMU escape on the Tianfu Cup in 2019. Without further ado, let me start his talk. He will have a live Q&A session, provided we don't get any more network issues. Again, we're sorry about that. But yes, keep your questions coming in Slido, Discord, and we'll bring it up at the end of the talk.
Hello everyone, my name is Tang Tianwen. My nickname is Victor V. My partner is Xiao Wei. Thanks for joining this speech. Let's start the journey of Breakout the Western World. I work at 360 Security Vulcan team. I majored in virtualization security for 2 years. I have found several critical bugs on VMware products and Hyper-V. Here is my partner Xiao Wei. He worked at a 360 Security Vulcan team too. He has won several virtualization escape challenges, including Workstation, ESXi, VirtualBox, and QEMU. Next, let me finish this speech. First, I will introduce virtual network device in VMware Workstation and ESXi. Next, I will introduce the primitives during exploitation. Then, we show 2 examples with these primitives. Furthermore, we will show a demo of escaping from ESXi. At last, we discuss what we learn and what is new in newest workstation. In this part, I will talk about virtual network architecture and its attack surfaces. Device architecture. Workstation and ESXi have similar architecture, so I don't make a distinction unless it's necessary. Look at this picture. We call a virtual machine as guest, the real machine system as host. Call the process in host which running a guest as VMX process. Each guest network driver communicates with the virtual network device directly by I/O operation, including I/O ports and I/O memory, and each guest is running in different VMX process. As you can see, virtual network device filters data from guest driver and send it to physical driver. Here is an abstract picture of VMX process architecture in VMware Workstation. There are 3 different virtual network devices shown in this picture. Each device has its own command analysis function and filter function. They use a common transfer function to handle network data. ESXi handles data in kernel instead of a user process. Guest driver use I/O operation and WebMap to translate commands and data to network device. So we know the bugs may exist in virtual network device when it handles data and command from guest driver. Adversary. There are 3 attack surfaces in virtual network device. First, if a virtual network device handles guest command data incorrectly, it will cause a problem. The case of escaping from workstation belongs to this. Secondly, if a virtual network device handles guest physical memory address incorrectly, it may also cause a problem. The case of escaping from ESXi belongs to this. Thirdly, if a virtual device doesn't check common data completely, the common data may transfer to host kernel, which may let host crash or worse. I have found a bug exists in VMC host driver. It may be published one day. When we find a bug, we should exploit it. But before we do it, we have to understand how a VMX process accesses guest's memory. Then I will introduce a way to heap spray, a way to read and write data between guest and host process, and a way to bypass CFG on Windows 10. Guest memory. At first, let's find out where the guest physical memory is. Look at the picture. The yellow rectangle represents process memory. Purple rectangle named WebMap represents guest physical memory. WebMap is a map space in process memory. In this picture, guest system can access WebMap directly, but WebMX process needs to translate a guest physical memory address into process memory address if it wants to access WebMap. In my thoughts, if the physics and size
is illegal. Address translation function should return fail. But, however, when X tries to allocate a 4K heap or an array to store translated address for each page frame number and return success. Let's see the code. On left is a structured definition of WAM-ADDRAW-TRAN. This structure is related with the address translation operation. On right, WAM-ADDRAW-TRANSLATE is a function for translating guest physical memory address to a process address. FID2Vert is going to check range of physical address and size and return the process address by adding WAM map offset with a given address. If FID2Vert runs success, it will assign the result to field Tang and return success. If else, if FID2Vert runs fail and the nums is equal to 1, it will try to allocate a 4K heap, or after 10 times fail, it will assign this memory to field Tang. We call this memory as H1. It's an important characteristic to leak data from host process to guest. When process handles a buffer from guest, if we can confuse the range of a translated buffer, we can overflow read or write process memory instead of WAM map. If the num is bigger than 1, it will allocate a buffer to store result for each page frame number, and the array pointer will be set to field 18H. Once the guest's memory has been handled, function WAM-ADDRAW-TRANSLATE-FREE will be called. In this function, it will free memory allocated before. Now let's look at an example. Look at the upper part of the picture. If we give a physical address and size like this, the given range is bigger than WAM map, so WAMX will allocate a 4K heap. Look at the lower part of the picture. If the sum of page offset and size is bigger than 4K, it will allocate a page array, stores at here. So now we know how WAMX translates address from guest. Next, we need to discuss exploit primitives. Heap spray. To make our exploit stable, we need to heap spray for heap layout. The easiest way is to use SVG shader buffer. We can decide its content and size, and we can release at any time. However, we can't change its content after the memory is allocated. The details of sending SVG comment, you can watch this proposal. They made a great work to explain the details, so we don't need to tell it now. SVJ has a mob structure that allows guests to transfer data between two mobs. The field, as you can see, the field of guest buffer stores the result pointer from translation function. So if we can overflow the size field of this structure, then we can overflow read and write between guest and process memory by this SVJ command. In WMX3 module, it's a default network device used in ESXi. We can use MF table to write data to a heap. We can control blocks data after the memory is allocated. And we can also control its allocation and release. SVJ GM buffer is a MKS heap. MKS heap is a special heap with an extra heap header. The header field looks like this. It has a field named header size. When freeing a MKS buffer, it calculates the real heap header by subtracting buffer address with the header size. So if we overflow a MKS heap header size field, we can free another heap. One way to bypass CFG is to change stack return pointer. So we need to find a skill to leak stack related address. After we can read and write everywhere, we can control SVJ function table. And let it call a special function which can set R9 from a global pointer, which we can control its value. Then let it call a short function like this. In this function, it will copy data from RCX to R9. And this SVJ call function, it uses a stack address as argument 1. So RCX is points to a stack address. So we can leak stack pointer to guest. Now let's start a real practice. ESXi is a Linux-like system, so we can assume that it's a Linux system. The following exploit steps based on Linux system's heap features. The bug exists in WMX3 module. Let's see this translate function. If the sum of phases and size is bigger than limit, it will return 0 without reset the data of this variable. And in WMX3IO handler, it calls this function without check function's result. And Then it will call a free function. In this free function we mentioned before, it may free a heap from stack variable. So this leads to an uninitialized bug. To exploit, we need to transfer it to an UF bug. Here is the details. Firstly, we give a run a physical address like this. Then the translation function will allocate a heap with size 0x60 and assign it to field 18H, and the heap will be freed in release function. Secondly, we allocate a MF table with size 0x60, and the heap should occupy the same space, because the space should be the first chunk in free list. Then we trigger the bug. It will free the pointer stored before, which points to MF table now. So we get a dangling pointer of MF table. Fourth, we allocate a GMR buffer to occupy the freed MF table. Then we allocate a mob with a 4K heap. With our heap control, the heap layout should look like this. Then we change the MKS header from this to this. And when freeing a GMR buffer, its function gets the heap address by minus MF table's address with header size 0x3010. So in fact, it doesn't free GMR structure. It frees the mob's heap block. Thus, we get a mob that points to a free memory. Sixth, we allocate a shared buffer to pad that 4K block, and the size should be like this. Then it will split a OX60 whole block. Then we allocate a mob2 structure. We allocate a new mob structure, we call it mob2, and it should be put at our hole. We let mob2 point to H1 because H1 is an early allocated block. It should have a lower address in memory process. Seventh, we use mob1 to change mob2's size field, so we can read and write host process data after H1. We can use SVG command to copy data between these two mobs. ESXi doesn't have CFG or railroad, so we can control its function pointer directly. We just need to find a dynamic call with control arguments. Here is a sample of control IP I used before. in SVG draw data draw comment handler, it will set v2 from a global pointer. Because we can read and write everywhere, so we can control its value. Then it will call this function, and this function, and this function. And the RDI is equal to A1. So we can control IP with our arguments. Because RDI is the first, it stores first argument or a caller in a next system. So we control the first arguments. Let's start another case. Let's say difficult the first time, easy the second time. Here is a bug function. I had some unnecessary codes, so don't confuse with the code logic. Data of memory is controlled by guest. At line 81, variable v17 is equal to variable 23. And v17 is a short, and v23 is a integer. So there is an integer truncation problem. And look at the line 91. Rest size is equal to variable v23. v17. If the value of v23 is bigger than 0x10000, then v17 must be smaller than rest size, and per size will be assigned with v17. So the rest size must be bigger than 0. So memory copy will be called, and it copies the data from mem to its end. And so here is the heap overflow. And there's another way to overflow data with a given offset. It's not shown in this picture. Because Windows has LFH, so it's a problem to arrange heap layout, but it's not impossible. Firstly, we allocate many mob blocks like this. It will fulfill a LFH block. And then we free several mob structures. So there are several holes freeing blocks in a LF chunk. And then we trigger the bug. If we are lucky, the mem and the mob should be adjacent, and it can overflow a mob size field. Thus, we can leak information from host process memory. We let all mobs point to H1, and the data after H1 should be leaked from mob. Then, after leaking process-related address, we overflow again. We change mob's pointer. Let it point to mob list. Mob list stores the address of mob structures. It's in our data segment. Then we fake a mob structure. Let its guest buffer field point to SVJ FIFO command scratch space. It's the SVJ command buffer at .r data segment. We can use this SVJ command to change its data. So we can fake any mob structures we want.
After previous steps, we can control a mob structure. It means we can read and write everywhere with 2 fake mobs, but we don't know the translated address of guest's memory. So we need to leak where map offset to guest firstly. To achieve this, we let a mob point to the address where stored where map offset. Then we use surface copy and surface DMA command to leak data from a mob to guest's physical memory. After this, we know what is the translated address of a guest memory. So we can fake 2 mobs. One points to somewhere we want to read and write. One points to our guest's memory. After this, we can read and write everywhere now. As mentioned before, we use this skill to bypass CFG. Here is the demo of escaping from ESXi. Now you can see I created a new file named T2. It's a root privilege. So what we know? Programs may be careless about the returned function results. Creating an extra heap header without encoding is not a smart idea. Manufacturers should add modern mitigation mirrors to their products. Like ESXi should add CFG or railroad. VM escape is not as hard as we expect. Virtualization security is still a serious problem at present. We should be careful. New change.
No?
To avoid
Victor,
to
I'm turning
abuse
on your
mob
video
structure,
now.
VMware Workstation 15.5.x stores mob structures in .r data segment instead of allocating a heap. But other primitives still work, and it's easy to find a similar structure in SVGA. At last, thank you.
Thank you for your talk. We shall move on to the live question and answer. Just give us a second while we transition to the Zoom channel. Hi, Victor. So there is one question. Can you hear us? Oops. Hi, Victor. So there
Hi.
is one question that there has been. What are ways that an end user can detect VM escapes?
Can type it?
Sure. Can you see it on the screen?
Where? Room? Oh. Mm, I think users can detect VM escapes in the host by monitor the process's behavior. If they call some dangerous functions like system or create new processes or something. So, and another way to detach, to check if they did some dangerous operations in guest system, like insert a host driver, a device driver or something. And for other situations, like they escape with some hack skills to create processes in host, it's hard to detach. If a hacker attacked the host's kernel bugs, so we can't detach it in user mode. That's my answer.
Okay, thank you. We have one more question. I have written it in the Zoom chat, but I will read it out as well. Can you explain your process on identifying VM escape bugs, and can you use fuzzing in the bug hunting process?
Process on identifying bugs. Well, like I said, we have to find some attack surfaces and keep following the process of handling user data from guest driver. And I major in reverse the bug. I reverse the process to find the bug in, and I'm not familiar with fuzzing, so I didn't fuzz. I don't use fuzz.
Okay, thank you. if there are any more questions, you could post it on the Discord channel and Victor will gladly answer it there. I think he's going to be hanging around the Discord channel the whole day. And now that would be the end of this session. We will be having a break between talks for lunch. Our next talk is scheduled to start at 2 p.m. for both track 1 and track 2. In between, if you feel bored, please do check out our virtual labs. We have the hardware hacking starting at 12 p.m. Oh, well, it's already started actually. That goes up till 2 p.m. So that should give you a good time to fill up in between the talks. The talk that starts at 2 p.m. in track 1 would be The Secret Codes Tell the Secrets by Zhang, Qing and by Guangdong. And in track 2, Exploring and Exploiting the SQLite Finding More Bugs by Targeted Fuzzing by Tianwen Jiang. We shall see you then at 2 p.m. Have a good day. Sorry, see you then.
Have a good day.
been up far too much lately. I have to stay home tonight.
She's in love with him. Very much. She's in love with him. Very much.
Hello to everyone still listening. We hope you've had your lunch and had time to go and check out the village as well as the CTF challenge. We should be starting our next talk in the next 3 minutes. The talk in track 1 would be the secret code tell lies. Sorry, the secret code tell the secrets. And we should start in 3 minutes. Stay tuned. If you need to go grab a drink or your food, do it now. Yep. Hello and welcome back. We are ready to start the second half of our first day of Hack in the Box Lockdown002 live stream. We have Dr. Bai and Dr. Zhang talking about the secret codes tell the secrets. A quick introduction about them. Dr. Zhang is a senior security researcher. He used to be a senior Android researcher at Qihoo 360 and visiting scholar of Model Checking Lab in National University of Singapore. His interests include Android security, IoT security, and payment security. His work has appeared in Syscan 360, Black Hat, Hack in the Box, and so on. In 2016, 2017, and 2018, he won whole year's first place prize in vulnerability detection of some major companies, including Samsung, Huawei, Meizu, and Oppo. Dr. Bai is a faculty member in the Singapore University of Technology. He received his PhD degree from NUS in 2015. His research interest spans across the broad areas of mobile security, web security, and protocol verification. During his previous research, he has worked on analyzing authentication protocol implementation, online payment, as well as Android security. His research has helped identify and fix serious vulnerabilities for major websites like Sina Weibo. His work appears in top conferences such as NDSS, Syscan, Hack in the Box, as well as Black Hat Europe. This will be a pre-recorded video, and at the end, they will be taking question and answers live. So without further ado, let me start their talk.
Hello, everyone. Welcome to our presentation. We are going to introduce you our work, The Secret Codes Tell the Secrets. Our presentation is divided into 4 parts. The first part is about ourselves. The second part is the topic, secret codes. And the third part is the vulnerabilities we have identified, which are related to the secret codes. And the last part, we're gonna leave around 10 to 15 minutes for question and answers. So first of all, about ourselves, my name is Guangdong, and I was in Singapore, but now I moved to the University of Queensland in Brisbane, Australia. And my research is on mobile security and protocol analysis. The left-hand side, Zhang, my partner, he is currently the senior Android security researcher from ByteDance, and his research direction is Android security and payment security. So this is actually the 4th or the 5th time that we give a talk in HITB, but it's a pity this year we cannot see you guys in Singapore, and so we have to meet all old friends. So the second part, the secret codes, which is the topic of this work. So I believe you have such an impression in your dialer. You don't have to every time. You don't have to input your mobile number here or phone number here. What you can do is you can input something start with star sharp and the code, then sharp star. So this is called secret codes, and sometimes it can be referred to as hidden codes, so or security codes. So if you see those stuff, they actually mean the same thing. So the secret codes in Android are well known by engineers and geeks, but previously people are just use them for testing or just for fun. And we're gonna reveal that actually security codes has lots of security implications, and this haven't actually been well studied and even have not received enough attention. But through today's talk, we're gonna show you that those secret codes actually expose many attack surfaces, which can be easily compromised by the attacker and to obtain the system privilege. So here is a very famous incident in 2017. A security researcher pointed out that from some Android devices, so here we omit the name of the brand, it's a brand with a lot of users. Okay, so the security researcher pointed out that such Android devices have a backdoor in an engineer mode app, which can lead to the root exploit. And later, the Qualcomm VP of Product Security Engineer, Alex, stated on Twitter that the engineer mode app was not authored by Qualcomm, but others, maybe the manufacturers, who built it on top of previous testing application. So this incident raised a very big concern. So it was reported on the website, and later in a Twitter, researcher posted that actually through the secret code, you can actually access the manual tests such as a GPS test and the root status test. And further, we're gonna reveal that actually a lot of more tests can be done through the secret code. For example, the fingerprint test. We're gonna introduce you later in this presentation. So we want to have a discussion on the Android permission system first before we enter secret code, because this is gonna, this is actually explain why the secret code can cause security problem. So we know that after Android 6, Google has tightened Android permission. For example, previously the permissions is granted to the applications at the installation time, but now Google allow a granting at runtime, which means whenever application wanna access sensitive data or sensitive service, such alert will be prompt to the user, and through this user can choose to grant or deny the access. And since Android 10 and 11, Google also give users interface to specify fine grant permissions for sensitive data and services such as location, microphone, and camera. So when we're talking about the access control system, one thing we need to make sure is whenever, when you protect a particular sensitive object, the permission policies must be enforced consistently and globally. So what do I mean by this? Let's say you have very sensitive service, and through the normal user interface, you have very comprehensive control on the authentication and authorization. However, if your access control system provides some special entrance, so that the user or developer or anyone through that entrance can access that functionality, then this is a violation of the existing permission policy. And to some extent, this kind of entrance can be regarded as a backdoor. So here, I want to show you a very quick example. So in this one, you can notice that through the normal interface, through the actually the settings application in the Android phone, if you want to change the language of the system, you will need to input a PIN number or pattern log. So basically, you need authentication to do that. However, if you do it through the secret code, actually you don't have to input any authentication or authorization stuff to prove your identity. Okay, so let's look at this demo. Yeah, so here is, when you do this through the settings app, you need to input the pattern or input the PIN. However, if you do this through the secret code, so this is a secret code you can use to change the language setting. Okay, so if you do it through secret code, what you can find is you don't need the pattern log, you don't need the PIN code to change the language, right? So here actually is something I discussed in the previous slide. You have the normal interface to change the language, and this interface will be enforced by authentication and authorization. Basically, there is a safeguard to this functionality. However, if you use a secret code, this safeguard can be bypassed. Okay, so this is a violation to the Android permission systems. Sorry. Okay, so now I want to have a very quick introduction on secret codes. The secret codes in Android refer to the codes we can access hidden features or secret menu, such as display information or to test hardware and software. And these codes are usually used to provide a faster way for the manufacturers. So be careful, here is manufacturers. That means this secret code is used only in a factory. So this code provides a fast way for the manufacturers to verify, their smartphone and tablets are working as intended. For example, if you want to look at your IMEI number of your mobile phone, what you need to do in Android is you go to setting and about phone and check the IMEI number. However, through the secret code, you can simply dial this code to get the IMEI number. Okay, so what will happen when this secret code is dialed in a dialer of your phone? So basically, the system setting or system dialer app will trigger this code. So in this code, you can find that it broadcasts intent, which include the secret code action. So later I will show you what is action, and then plus with a data field which include the actual secret code. Okay, so this thing will be broadcast so that any application which listen to such type of intent will get this constructed intent here. Okay. So you can actually create your own secret code. What you can do is you can just put these lines of XML code into the Android manifest.xml. So basically, it registers a broadcast receiver for this application. You can find that the action, which is the one I just mentioned in the previous slide. The action is set to Android.provider.telephony.secret code, and the data field is a secret code you want to specify. Okay, then in your application, you just implement such a broadcast receiver so that whenever this secret code is dialed in a dialer app, this broadcast receiver will be invoked by the system. So you find here, this invocation is actually through the intent. It's not a direct call in a program. So this provides attacker opportunity. So if you're familiar with, how the application, how the ICC works in Android, I believe you understand what I'm talking about, which means this thing can actually be done automatically instead of require the user to input the secret code through the dialer app. So what you can do, first thing, you can just construct such an intent with the action, dialer action, and the secret code. Then you can just call the start activity. So once you call this intent will be sent to the one who is listening to this intent. Similarly, you can construct a broadcast to do this. So I hope you find the trick here is the attacker doesn't have to actually input anything through the dialer. It can construct such application so that it can automatically, by automatic I mean it doesn't need the victim user's interaction. It can automatically call the application which dealing with these secret codes. Okay, so why this is risky? Why is this dangerous? Basically, those secret codes come from those factory installed application, such as the engineer mode or WT secret code manager, and some are from those embedded applications such as the contacts, calendar, and even the calculator. So the special thing for those applications is that they are either built-in or system-side, which means they own very high privilege that different from the normal application. Basically, there are those applications with the highest privilege in the mobile phone. Okay. So what does that mean? That means once those secret codes can activate those applications to do some actions, those actions actually high privileged. Through a normal application, definitely those actions cannot be performed, right? So you can find that those secret codes can provide broad attack surfaces and cause severe security impact to the users. So as evidence, if we grab this is the action, the interaction name I just showed you. If you grab this in the devices, you can find that all the applications with this action, basically all the applications which handle the secret codes are actually in a framework directory, which means there are those applications with a system or signature level of privilege. Okay. So we categorize those secret codes into 6 categories. So the first one is the info code. Basically, through the secret codes, it's possible to get some sensitive information. For example, the *#06#, the one I just mentioned, display the IMEI code of the mobile devices. The second type is a backup codes. So you can find one here, one long one, which do a quick backup to all the media files in a mobile mobile devices. And the third category is the testing codes. So this is used for tests. Basically, a lot of vulnerabilities is related to the secret codes in this category. So later I will show you that. An example for those testing codes, secret codes, this is fingerprint test. Okay. The first category, the configuration codes. So basically, it can do some configuration on the phone. For example, can do a complete wiping of the mobile devices. And also it can reinstall the firmware of the mobile device. The fifth category, the developer codes. So basically, it provides several secret codes can be used by the developer to fast reach a position during the development process. For example, system dump mode. And the last mode, USSD mode, is related to the phone call. For example, these 2 secret codes can be used to turn on or turn off the call waiting. So the purpose we list those secret codes to you is that we want to show, actually those security codes can do a lot of high privilege actions. Okay. So next part, we're going to introduce you the vulnerabilities we identified, which are related to the secret codes. So as a very quick summary, we identified 5 types of the vulnerabilities. So what we will do in this part is, I will first give you a very quick brief on those 5 categories of vulnerabilities. Then Qing is going to give you a demonstration and explanation on a demonstration. Okay, so the first part, the first type of vulnerability is kind of the system reset bypass vulnerability. So what do I mean by this is, if you want to do the formatting and factory resetting on your Android device, it's very sensitive, right? It's very risky. It usually requires you to do the authentication. However, we find that through the secret code, actually, you can bypass the authentication part. And this vulnerability, is the most severe one we find, and it influence basically all OEMs devices. And fortunately, the problem is gradually fixed by manufacturers as the Android OSs are upgraded. Okay, so later we'll give you the demonstration. The second type of vulnerability is the something related to using engineering mode to change the language settings, like in the first few slides I introduced. And also some vulnerability allows to turn on cameras without users authorization. So this is very dangerous, right? Because it basically leaks users' privacy and also the information of users' surroundings. So it's very privacy sensitive. And third category, we find that some devices might, once the application is caught by secret codes, they may just lock the ping through the lockcat. So later we will show the examples. The fourth category is to some devices allow to use the engineering mode to reboot the phone into Qualcomm's kernel FFBM mode, which is a very dangerous mode. Later I will explain it to you. The last type of vulnerability is to use the engineering mode to reset and disable the fingerprint lock. So basically it's to bypass or to disable the fingerprinting authentication system in your mobile phone. Okay, so next we're gonna give you a demonstration for each category one by one. So I will invite Qing to give you the first demo. Hi, Qing.
Hello, everyone. I'm Zhang Qing. Here I will show you several vulnerabilities about the secret codes. The left one was found a long time ago, assigned this V number. From this video, we can see if we want to reset the phone from setting application, it needs your authentication. But if we type the secret code directly in the dial UI, it does not need anything. Okay, let's see the first video demo. Okay, the second demo on the right can show the inconsistency about the permission more vividly. We reach the engine model interface and find that there is a reset phone function on the first page. If we click it, it pops up a dialog, which is needed to input the password. Then we go back to the first page to click the engineering test and select the third tab. Here we can see another reset function, from where it does not need any authentication, but pops up another dialog, which says the config file is not existing. We try to attach an empty config file in the SD card and click the reset button again. The phone is reset. The OEM is applying a CVE for this one. Okay, let's see the video demo. Okay. Let's say another page. Let me show you a demo about the leaking lock screen pin number. It happens in the same place, just the last one. If we type the password to reset the phone, the password will be printed in the logcat. What's more, at this moment, the user's PIN number is removed. Because of this activity is spotted, there is existing the third vulnerability. An attacker can use any application to invoke this activity to induce the user to remove his password. Okay, let's see the video. Here we go back, we find the password is removed. Okay. Let me show you another about leaking user's password demo. This demo is also about the leaking user's Wi-Fi password. We find that there is an exported broadcast receiver in the engineering mode, which can receive the connection Wi-Fi broadcast to connect to Wi-Fi, in which it prints the SSID and the password to the logcat also. Okay.
Okay, thanks, Qing. So next part, I'm gonna give you a very quick introduction to vulnerabilities related to the engineering mode. So just now we mentioned that secret codes can change the phone into engineering mode, and this is very dangerous. And why? I'm gonna introduce you soon. So before that, I will quickly introduce you the FFBM mode, which is kernel mode called fast factory boot mode. So this mode is developed to be used by the manufacturers, and is used to facilitate fast reboot and testing in a factory. So it only provides very minimal user interaction, so that it can be reboot very fast compared with the normal Android operating system. So on the right hand side, this flowchart gives you a very quick introduction on the booting process into the kernel FFBM mode. So you can find that once the kernel is started, and it will execute the init process, and here instead of boot into the Android mode, which is more expensive, more heavy, and we can choose to let the phone boot into the FFB mode during the development in a manufacturer side. So after the problem is that after entering into the FFBM mode, the user has to quit it and re-enter the normal Android mode. So this is the 3 steps. The user can do that. But the problem is the second step is actually very, very risky. So basically, before quit the fast boot mode, you need to erase the MISC partition. So we know that there are lots of crucial system configuration information stored in a MISC partition, and also like CID or USB configuration, and even some hardware configuration are all stored in this partition. So it's safe to remove it, to clear this partition in a factory, because there's no any sensitive data stored. But the problem is, once the phone is already used by the user and some information are already put in that partition, then if this partition is erased, there will be some problem. For example, the phone may be, after you reboot into the normal Android mode, maybe it cannot function as normal. Okay, so secret codes can actually enter this, engineering mode, which is on the left-hand side. And if the user, if unsuspecting user just choose to reboot to the FFmpeg mode, the problem which I mentioned in the last slide will happen. And the last vulnerability I want to talk about is regarding the fingerprint checking on a fingerprinting-based authentication system. So basically, through the engineering mode, you can enter the fingerprint test. But the problem is, once you do the test, the test, right, is a test. It shouldn't pose any side effect to the normal side, right? But the problem here is, if you do such test in an engineering mode, the operation you do on the fingerprint may affect those fingerprints in a normal mode. So here is some complaints we find on the forums posted by different users. So they all complain one thing. They did a fingerprint test in the engineering mode, and then they find that normal fingerprint-based authentication is disabled or dysfunctioned. Okay, so here is how this will happen. So once you enter the engineering mode, and if you choose the fingerprint test, and this is a screen where you can, record your new fingerprint, but whatever you do here is gonna erase the stored fingerprints. So basically, this is bypass authentication bypass attack, right? So that is all about the 5 categories of vulnerabilities we identified in this work. And before I start answer your questions, I want to give you a very quick introduction on how we identify those vulnerabilities. So basically, we built a fuzzer to do this. And what we do is we get the application list in a mobile device. And then through the context resources, we can get their Android manifest.xml. And through a very simple parsing, we can find those applications which listens to the action, the action name of the the secret code intent. So the one I showed you in a few slides before. So once we get this, we know which applications actually handle the secret code. So what we do is, we get the code name, and those numbers, those string 1122, those stuff. We get the name from the manifest. Then we can build a proof of concept to test application. Okay, so this is how we have identified the vulnerabilities we reported in this presentation. Okay, so we come to the summary of this work. Basically, we want you to take away a few recommendations. The first recommendation, when you design and implement access control system, make sure is consistency. Basically, for a particular sensitive object, so all the paths with this object must be enforced the same access control policy, right? So the basically the access control must be consistent. And the second is just for the developer to make sure you remove all the such secret codes or the backdoors, because definitely they will be identified by the researchers. And last, remove all the functionalities for testing in factory. For example, the engineer mode app. Basically, they are just used to for the efficiency in the factory. There is no sense they need to be given to the normal users. So what we suggest is, all the manufacturers should consider removing those functionalities before their mobile devices go to the market. Okay, so that is all for this presentation, and thank you so much for your attention. And next part, we are happy to answer your questions. Thank you.
Thank you, Dr. Bai. Let's go to the Zoom session for the live Q&A. Just give us a minute while we transition to that.
Okay.
And we're live with Dr. Bai. So, Dr. Bai, we've got 3 questions for you. The first is, they're saying, thank you for the presentation. Very fun and creative attack surface. In your opinion, what can Android OS implement to prevent mobile phone vendors from leaving leftover debug secret codes? Sorry, I was talking in mute. Hi, Dr. Bai, can you hear us?
Hi, streamer.
Yes,
I can
hi.
hear you.
Okay, sorry, I was talking in mute earlier on. Okay, so we've got 3 questions for you. The first is, thank you for the presentation. Very fun and creative attack surface. In your opinion, what can Android OS implement to prevent mobile phone vendors from leaving leftover debug secret codes?
Oh, okay, that is a really good question. So I think I can answer these questions from 2 aspects. Yeah. Later, if Zhang want to add on, please feel free to do so. So the first aspect is from the vendor's perspective. We suggest the vendors to remove all the apps or all the functionalities that's just for testing in the factory before the mobile devices go to the market. And the question is regarding from the AOSP perspective, what can be done? I think one thing can be done is to add a permission. So which when whatever app wanna set such intent, the intent we show in a presentation, there should be a guard there. So basically, I think that is the what AOSP can do. But I think the fundamental solution is for the vendors to remove those testers, those testing, debugging mode functionalities, because even AOSP adding the permission are still possible for the vendors to remove the permission. Yeah, so that is the question from my side. Yeah, so Qing, if you have anything to add.
Okay, that's enough.
Okay, yeah, thanks.
Wonderful, thank you. We have another question. What Android permissions are required for an application to use secret code to invoke functions and craft Android intent to input secret code?
Yeah, so for this one, no, as we showed in the slide, if you still remember the code in Android manifest.xml, you can find there's no permission to protect those intent at all.
Okay, anything to add, Dr. Qing?
Thanks.
No, thank you.
Okay, we've got 2 more questions. The next one is, how do you analyze all the functions that handle secret code? Do you use any automation in the bug hunting process?
Oh, okay. So we mentioned it a bit in the very last part of the presentation. Basically, it's semi-automatic. We can do a automatic filtering. So basically, we scan all the manufactured file and find out the application which take or send the intent related to secret codes. And the next part for the logic, basically, I mean, when a secret code is received by an app, what will be done? That part is that part was analyzed manually. Hope this answers your question.
Dr. Qing, anything to add?
Oh, okay. The thing, I don't have any to apply.
Okay, no worries. We've got one last one. It's more of a
sure.
question not on the subject, but we'll ask it. It's from Anonymous as well. Xiaomi is ranked second most popular mobile brand in 2020. Do you think Xiaomi will rebrand to Dami when they reach number one?
Okay, that is really a question that I cannot answer. Qing, you have any thought on this question?
I have no idea about this.
Yeah, it's very interesting question. But I mean, we also contribute a lot to Xiaomi's device security. But it's very hard for us to make an estimation on this. So sorry, but yeah, we are happy to contribute to the security of Android devices.
Right.
Any brands? Yeah.
And we're all happy to have you contributing and keeping us safer. Right. I think that's all the questions we have so far. We'd like to thank you again, Dr. Bai, Dr. Qing, for this wonderful presentation.
Thank you, Sriman, and thank you all the audience for your attention.
Right. So our next talk would be at 3 p.m. Singapore time. It would be a journey into the secret flaws of DRAM RowHammer mitigation by Emanuele Vannacci and Pietro Frigo. So don't go away. Join us again in 15 minutes, and we'll see you then. Hello to all viewers. We'll be starting our next talk in about 5 minutes, entitled A Journey into the Secret Flaws of In-DRAM RowHammer Mitigations by Emanuele Vannacci and Pietro Frigo. Hello and welcome back to our fifth talk of the day for track 1. Up next we have Emanuele and Pietro who would be talking about the secret flaws of In-DRAM RowHammer mitigation. A quick bio of them before we start. Emanuele is a PhD student in the Systems and Network Security group at WUSEC. I would try to pronounce it, but I'll probably offend some people, so I shall not. He previously received his M Engineering from the University of Rome. His research focuses on hardware and software security, microarchitectural attacks, as well as side channel exploitations. Pietro is as well a PhD student at WUSEC, VUSEC. It's the VRIJE Universiteit of Amsterdam. His research focuses on hardware security, investigating attack vectors such as RowHammer and side channels. He was behind the first WebGL-based RowHammer attack, and recently involved in the discovery of Intel's MDS vulnerability. This would be a pre-recorded video, but both of them will be with us live to answer questions at the end of the talk. So without further ado, let me produce their talk.
Hi everyone, I'm Pietro Frigo, and today I and Emanuele are going to present our talk, A Journey into the Secret Flaws of In-DRAM RowHammer Mitigations. First of all, who are we? Well, we're both PhD students at WUSEC, which is the system security group at the Vrije Universiteit in Amsterdam. And the two of us have been investigating RowHammer for the better part of the past 4 years. Today, we're going to discuss the results of our last 2 years of work on this topic. So what is this talk about? Well, clearly, this talk is about RowHammer, and I guess you could have imagined that. But more precisely, in this talk, we'll focus on what was supposed to be RowHammer-free DDR4 memory. Indeed, memory vendors claim to have solved the RowHammer issue once and for all by introducing In-DRAM mitigations. So today, we'll dive into the details of these solutions that were previously unknown, and we'll tell you how we reverse engineer them. As you can imagine, we wouldn't be here today if we didn't break them as well. So we'll then tell you how we did that, and we'll touch upon their effectiveness. But to discuss their effectiveness, we need to first understand what was available out there as a possible defense. So before doing all this talk about the new In-DRAM mitigations, we'll discuss about both software and hardware mitigations were being proposed in the past. Now, since in this talk we're going to go into the details of a lot of this DRAM circuitry, we'll now give you some context and some background information about DRAM and RowHammer itself. So let me start with DRAM. When you think about DRAM, you usually think about something like this, which is a DIMM. And you know that somehow the data is being stored in here, right? Well, the data actually is being stored inside these ones, which are the chips. And inside the chips, you have another structure, which is called bank. And every chip contains multiple banks. Now, a bank is simply a bidimensional array of memory cells. And a cell contains a capacitor and a transistor. Now, the capacitor is where your data is being stored, whereas the transistor is the gate to this data. Every cell contains a single bit of information. And when you want to perform memory operation on this data, you need to rely on these other two circuits, which are the row buffer and the row decoder. And now we'll see how these are being used. So let's take one step back and let's consider your normal C program where you say you want to perform the reference of a memory address, right? Now the CPU can handle these addresses, right? But then when you take into account the DRAM subsystem, this address doesn't mean anything for DRAM itself, right? So what you need to have is another component inside the CPU, which is the memory controller, which basically acts as a bridge between the CPU cores and the DRAM subsystem itself. And what it does as a first task is translating these addresses in something more intelligible by the DRAM chips. So, for instance, in this case, the address A1 will translate into bank 0 and row 1. Now, after the memory controller knows that this is the real address you want to access inside memory, it will say, okay, I want to perform a memory read or a memory write at this address. So we'll just communicate over the bus. So now, let's go back inside the bank. In the bank, now we're inside bank 0, clearly, and you will get to the row decoder an operation which is called activate to row 1. An activate command is what is needed to perform any operation on the data being stored in memory. And it consists in basically bringing the data down to the row buffer. And this happens by basically toggling the voltage of this line, which opens the transistor that blocks the data. And once the data is there, it will be connected to the bit lines, which is the one connecting it to the row buffer itself. Now, once the data is in the row buffer, you basically discharge the charges of the capacitor inside your own row. which means that the data is not stored in the row anymore. So what you need to do to prevent data loss, clearly, is to restore the data inside the cells themselves. And this is done by another operation, which is known as precharge. And the precharge command is basically the inverse operation of an activator. And what you do basically is, once again, you toggle the word line, and after that you change the voltage on the bit line so that the data will flow back into the cells themselves. Now, since the data inside memory doesn't last forever because the capacitor leak charges over time, the memory controller is also in charge of performing another operation, which is the refresh operation. And the refresh operation is basically an activate followed by a precharge. And this basically allows the DRAM subsystem to maintain the data for a longer period. Now, by DRAM standard, it is defined that memory vendors need to provide a retention interval of at least 64 milliseconds. And this means that inside the bank, the memory controller needs to refresh every row every 64 milliseconds. Now, clearly, if we would do that at the end of a 64 milliseconds in retention interval, this would create a denial of service attack on your own DRAM subsystem, because it would mean that at the end of the 64 milliseconds, you wouldn't be able to perform any other operation apart from the refresh. So what the memory controller does is it batches the refreshes in smaller batches, and it refreshes only some rows every 7.8 microseconds. And 7.8 microseconds is known as TREFI, and TREFI is one of the parameters that are defined in the DRAM standard. Now, what about RowHammer though? Well, as we said, DRAM is supposed to retain the data for at least 64 milliseconds, right? Well, what researchers have discovered is that if you perform specific access patterns inside DRAM, you may be able to trigger leakage a bit faster than that. And the most common access pattern, which is known as double-sided, consists in accessing two aggressor rows. And these two aggressor rows wrap in the middle another row, which is the victim row. And if you access them fast enough, you may be able to trigger leakage in the middle row much faster than the 64 milliseconds. Which means that if some cells are more vulnerable, you may be able to trigger data corruptions in the rows in the middle. Now, why is this important for security though, if they're just spurious errors? Well, it turns out that they're not really an error that happens randomly. But indeed, if you find a cell which is usually prone to fall victim of RowHammer, you can trigger this bit list multiple times, which means that this bit list is actually repeatable. So after its initial disclosure in 2014, the security community picked it up quite fast and understood the potential of this vulnerability. And the first thing they did was trying to figure out what could you do with it. So they tried to figure out if you could bypass the common privilege boundaries, such as a supervisor or a hypervisor. And the first exploit came out just 1 year after its first disclosure by Google Project Zero. And basically was able to gain root privileges by a normal application running on the system. Not so long after that, multiple exploits showed it was possible also to break the separation between kernel and hypervisor. And not only that, but people have shown it was also possible to trigger bitlists from a sandbox environment. And this brings us to the first axiom of RowHammer, which is privilege boundaries are a social construct. Now, apart from this joke, this is actually quite serious because as we just saw in this previous slide, what this all translates to is basically the death of memory integrity. So after we state memory integrity is dead, the question then becomes, how can we get it back, right? And this is where we start with looking into defenses. So the first stage of the defenses are clearly software-based defenses because they're the easiest one to deploy. And the first one that got proposed right after the discovery of RowHammer was disabling flashing instructions. And what do we mean by that? Well, as we said, in the CPU, you have the core that performs memory accesses, and the memory controller takes care of these ones, right? So in your code, you would have simply a tight loop with a reference of 2 pointers belonging to two different rows, right? Well, it's not so easy because after you perform the first access to these two rows, data will be stored in the cache. And if the data is in the cache, this means that the channel from the memory controller to DRAM gets disrupted. But luckily, in most modern architecture that are available today, you have explicit flashing instructions to invalidate the data inside the cache, like the CLFlash instruction. So if you use the CLFlash instruction, you basically remove the data from the cache, and this allows you to trigger bflips once again, because you go back to memory to fetch the data every time. Now, clearly, the first defense that was proposed was, well, what if we disable this flash instruction? You disable the flash instruction, you break once again the channel between the memory controller and DRAM, right? Well, not really, and we already saw it implicitly when talking about all the different exploits. And this is, for instance, when you perform an exploit from a sandbox environment. From the browser, clearly you don't have access to this CLFlash instruction. And how you do this is by performing, for instance, cache eviction. And this consists in basically trying to push out the data from the cache, so the cache lines that contain row 1 and row 3 will be pushed out of the cache so that you can access it once again from memory. And apparently this is already fast enough to trigger bflips. So this mitigation doesn't really work. Now, another option that was proposed was to perform tracing via the PMU. And the PMU is the performance monitoring unit. Now, the idea is that the CPU contains a whole bunch of counters that allows you to observe events on the CPU. And the idea you would have in mind is you want to observe accesses to memory and try to detect anomalies in these accesses. Luckily, most of the CPUs nowadays provide a whole bunch of different counters that counts misses in the last level cache, or memory requests. And by just observing these counters, you can see if you have an abnormal number of requests to memory. And the idea is, after you observe this thing, what you will do is try to refresh the rows that are being targeted, right? Now, the problem with this idea is that doing tracing from software is actually quite expensive. And for these reasons, you clearly need to trade performance for security. How would you do that? Well, the easiest way to do that is to tailor to specific patterns. So for instance, what you could do is trying to detect when someone is doing double-sided or something else. And this clearly, and it has been proven in the past, it's very easy to fool. Because if you tailor your tracing mechanism to specific patterns, then everything that deviates a bit from the standard pattern, it will not be detected. So also this one was not really an ideal situation. So then we just saw that basically it's very hard from software to prevent bflips from happening. So the next stage that came out in this history of software defenses against RowHammer was, well, if you cannot prevent these bflips, can you at least stop the exploitation of these bflips, right? And it sounds kind of reasonable. And the way this was proposed was by trying to propose physical memory separation. So what do they want to do was basically trying to enforce the same separation level that, if, for instance, you have in the CPU between different user space or supervisor levels, and basically enforce the separation also inside DRAM. How would you do that? Well, the way you can do this is by placing some guardrails in between the different privilege levels. So what you would do is you will store all the application data above the guardrail, for instance, and your Linux kernel data below the guardrail. Now, this theoretically should prevent attacks from EL0 to EL1. However, this doesn't prevent attacks between different applications in the same context level. So, for instance, multiple applications could attack themselves. So you could trigger a bflips from your browser and attack, I don't know, your Word application or whatever. And so this is already theoretically should be better than nothing, but still you allow a whole different bunch of attacks. Another solution, which was a bit more fine-grained, was to try to basically get this idea and make it a bit more precise. So the idea was to have a guardrail in between every other safe row. Then in your physical address space, what you would do is remap this memory into two regions, which are a safe region and an unsafe region. And the kind of neat idea behind this proposal is that you don't need to throw away the data in the unsafe region, but you just need to check for its correctness, right? So you would consider the safe region as your main form of memory, where you store most of your data. And on the unsafe region, you would store data that either you care less or you use less often. And then before accessing this data, you would rely on error correction or just some error detection mechanism to figure out if the data was corrupted. Now, what are the limitations behind these solutions? Well, first of all, the first limitation is that bit flips can occur on rows farther away as well. And because of this, it means that basically you might need to have way more guard rows than what you expect, which means that the performance impact are quite high. If, for instance, if you want to use the approach of doing the safe and unsafe region. And the second limitation, which is probably the most problematic for most of the software solutions that we discussed here, is that the fact that inside the memory you might have some unknown geometry of the location of the DRAM rows. So what is the problem here? Well, earlier we were talking about DRAM rows, and we were saying that basically when you perform an activate command, you will open a single row. Well, actually, that's not exactly what happens inside DRAM. But indeed, inside DRAM, what you have, you might have the same row wrapping around into different rows. Now, this is completely oblivious to the CPU and the memory controller itself. So the memory controller will still send an activate command to a specific row. However, inside DRAM, the circuit might be designed differently, and the data you will get is the correct one, clearly, but you just don't know where the data is coming from. And for these reasons, though, since you want to implement the defense from a higher level, so from the software, you should be aware of these different designs. And this becomes kind of unscalable because if different vendors implement different remapping strategies inside DRAM, it's impossible to keep track of all of them and figure out how to do this. So also this solution is not really ideal. So this is all for the software defense side, and we saw that none of them is actually as effective as they were meant to be. Now I will leave the floor to Emanuele, who will discuss with you most of the hardware defense that have been proposed in the past, and then we'll take it over and dive into the details of the new In-DRAM mitigations. Emanuele, take it away.
Hi everyone, I am Emanuele Vannacci, and during this second half of the talk we are going to discuss and explore a different class of defenses, or rather we are going to talk about hardware mitigations. So the first mitigation we are going to talk about is ECC. ECC memories are kind of memories that are mainly deployed in server environments. How can we find if a memory module supports ECC without looking at the specifications? Well, it's pretty easy to recognize ECC memories because if you look at the physical module, you can find an extra chip compared to non-ECC memory modules. And on this ECC chip, the memory controller of the system stores extra information, allowing the system to correct and detect errors. In current designs, the only ECC-aware unit on the system is the memory controller, and when the CPU wants to write some data in memory, the memory controller itself appends a certain amount of extra bits of redundant information for error correction and detection. So server memory comes with this capability. If an error is detected, for example caused by a RowHammer attack, the error can be corrected. ECC systems can correct one error, while for example a 2-bit error causes a denial of service. However, recent work shows that it's possible to trigger bit flips in such a way the errors are undetectable and uncorrectable, making the attack even more dangerous than a denial of service attack. However, ECC is not spread in its desktop environment, where it's easier to find another class of mitigations, and I'm talking about refresh-based mitigations. One original RowHammer countermeasure proposed is the adoption of a double refresh rate. That means refreshing all the rows in the DRAM every 32 milliseconds. So basically, the memory controller issues a refresh command every 3.9 nanoseconds instead of every 7.8 nanoseconds. While in practice only a small percentage of systems adopt a double refresh rate by default, Modern systems allow, for example, to set up the refresh rate by the BIOS, or even in the JEDEC standard, it's specified that when the DRAM temperature exceeds 85 degrees, the system automatically turns into a double refresh rate. During our research, we often had to check the actual refresh rate, and a way to do it is by timing analysis. Indeed, timing a long sequence of accesses in DRAM and looking at the latency peaks caused by refresh operations reveal the refresh rate. And for example, in the plot, in the current slide, you can see that a double refresh rate results in some latency peaks. So looking at the blue plot, that is a standard refresh rate, it's clear the difference with a double refresh rate resulting in twice the amount of peaks. Largely has been shown that doubling the refresh rate could not completely mitigate RowHammer effects, and we confirmed these results. Indeed, even shorter refresh interval, a longer refresh interval, could be necessary. And increasing the refresh rate does not come for free. Indeed, frequent refreshes cause performance degradation, mostly in terms of energy efficiency. So nowadays, modules spend 2 to 5% of the time just performing refreshes, and increasing these numbers to 10 till 35% will not be feasible, not for laptops, not for smartphone where you would see your battery life dropping faster, not for data centers when energy consumptions are important and must be taken into account. These are the main reasons why doubling the refresh rate is not an optimal solution, and it's rarely considered. So another solution is called PARA, aka probabilistic adjacent row activation. So PARA tries to reduce the number of refreshes required to mitigate the RowHammer, and to do it, it defines a parameter P. So P, it's a probability, and every time a row is activated and then closed with a certain probability P, the adjacent rows are activated. The main advantages of PARA is that it is stateless, meaning that it doesn't keep any counters or data structure, and so also the overhead is very low. However, the main disadvantage is that the memory controller has no knowledge of the memory geometry that is required to refresh and to activate the adjacent row. But we have also other kind of mitigations, and can be noticed how the trend through the mitigation design is to reduce the number of refresh operations more and more. So we started with a double refresh frequency when the memory controller issues refresh operation to refresh all the rows in the DRAM array twice compared to a standard refresh rate. Going through PARA, where you define a parameter P trying to limit the number of refreshes. And then the natural step forward is to try to refresh only the victim rows. So try to identify RowHammer attempts, identifying which are the aggressors, and then refresh only rows that are likely victims. So let's talk about PTRR, or pseudo-target refresh. That is a mitigation introduced by Intel to protect DDR3 systems. And the key idea is that the memory controller must monitor row activation and then performs a targeted refresh on the victim rows. The disadvantage here is that no details are available. The only source of information is an Intel presentation that you can find online. And here I reported a snapshot of this presentation where it's defined also the concept of compliant DDR3 DIMMs that is unknown what it means. What compliant DIMMs means? The answer can be found in the serial presence detect. So the serial presence detect is a read-only memory chip on the DIMM itself, and it contains some information, like for example information about the manufacturing date, about the manufacturer, about the timing constraints of the DIMM, of the DRAM, and also it includes this field called MAC, Maximum Activation Count, that specifies how many activation a row can afford before the adjacent rows start experimenting bit flips. And this maximum activation count can take three different kind of values. The first is untested, meaning that the MAC is not available. Unlimited, meaning that the DIMM itself is RowHammer free. And this is interesting because it could mean that the DRAM substrate is not vulnerable to RowHammer, but it could also mean that there are other mitigations in place. They're directly implemented in DRAM, and we will investigate this option later. Or a discrete value, for example 300K. So we carry out an experiment to see if the pseudo-targeted refresh is really implemented. So we picked up two machines. The first one is the one reported in the Intel presentation, and the second one is a desktop machine. So with a MAC value set on unlimited, the amount of flips that we could observe is pretty the same, but setting the MAC value to 400K, we could see a dropping in the amount of flips on the Xeon machine. And this leads us to conclude that pseudo-targeted refresh were actually working on the Xeon machine but not on the desktop machine, and that the DIMM itself has a capability to support pseudo-targeted refresh. But we tested also other machines, and we could conclude that pseudo-targeted refresh is a mitigation that is supported but is mainly dormant and disabled in most of the systems. But why? The answer is that probably there are other mitigations like target refresh. Now we are going to investigate another class of mitigations. So far we have seen software mitigations and mitigation that work with memory controller support, but here we are going to investigate the DDR4 landscape and the In-DRAM mitigations, so mitigations that are directly, completely deployed and implemented in the DRAM circuitry without any support from external components like the memory controller, for example. And here you can see in this slide a timeline describe the introduction of targeted refresh-like mitigations. So pseudo-targeted refresh has been introduced in 2013 to protect DDR3 systems, but it's possible to find it also on the fourth generation DDR4 devices. While we analyzed a batch of 42 devices, we could speculate that in-DRAM targeted refresh has been deployed only starting from 2016. And for two reasons, our batch, we decided to analyze memory built mainly after 2016 and one DIMM after 2015. So previous reports of bit flips on DDR4 devices questioned the effectiveness of target refresh, and this is the reason why we wanted to investigate more target refresh design. But what is target refresh? So target refresh is not a single mitigation, it's more like an umbrella term. Umbrella term is like a concept, and it defines an umbrella of mitigation that try to track row activations and prevent errors. How? Targeting refreshing victim rows. So there is no support from the memory controller because also the memory controller has no knowledge of the memory geometry, and the solutions are completely embedded in the DRAM circuitry. Targeted refresh was originally introduced with a JDEC DDR4 standard, but then it was removed in the revision B. However, memory vendors are still advertising RowHammer free memory modules. And this because they are likely implementing and deploying their own solutions. And so the landscape is so fragmented and there are no details because vendors are enforcing the security by obscurity principle. And this leads to difficult to evaluate the effectiveness of target refresh since no real evaluation and assessment is possible. So to study target refresh design, we decided to abstract from the single implementation, and we identified two components that target refresh design should include to work properly. And the first one is the sampler, that is the component that monitors row activations and inform other components about which rows must be refreshed. So for example, the inhibitor get this information and it can decide to refresh victims, or it can perform other kind of action, like for example remapping. And in this example, we can see a target refresh controller with a sampler and an inhibitor that they communicate. And the sampler, you can imagine the sampler as a cache, and when a row address is specified, the row address fill one empty slot on the sampler. And then when we can go on, for example, specifying row 7, then row 0, and then row 1. And at this point, when we specify another address, one slot must be evicted from the sampler. And so we can evict also row 7. And if we repeat this sequence of access, we can, for example, hammer row 5 and row 7. So we can evict them from the sampler, and when the inhibitor will ask for our row address to refresh, it will get, for example, R1, but we want to hammer, for example, row 5 and row 7. So this is just an example. To better understand how target refresh works, we needed to reverse engineer our DIM implementations, but reverse engineering poses some challenges. First of all, analysis from the CPU side is not feasible anymore because the memory controller provides a very high interface. We cannot specify sequence of commands, we don't have control over optimizations, and we don't have side channels. Because the DRAM is a synchronous device, operation must rely on specific timing constraints, and so we don't have any timing signal. We will need an FPGA-based memory controller, and we found it in SoftMC, an FPGA-based memory controller infrastructure, allowing us to issue specific sequence of commands like row activations and refresh command. So we want to reverse engineering the sampler size, how? Issuing specific commands by SoftMC, and of course targeting more than 2 aggressor rows because we want to fill the sampler and see what happens. We discovered a new hammering pattern that we dubbed the many-sided RowHammer, in which we basically pick n aggressor rows with n greater than 2, and these are our aggressor rows. So we hammer from 2 to 20 aggressor rows, in contrast to the state-of-the-art hammering pattern. Why? Why it should be clear? To lead the sampler to discard a few rows and then to get flips. So our methodology, we designed an experiment. We picked n aggressor rows, we perform a series of hammers, let's say 8k activations, and after each series of hammers, we issue R refreshes. This for 10 rounds, and then we looked for RowHammer bit flips. So, after our case studies, we could conclude that target refresh is enabled and it's mitigating RowHammer on every refresh command. So it's acting on refresh command. On every refresh command, the sampler picks some row or the inhibitor refresh some other row. And the mitigation can sample more than one aggressor per refresh interval. So on every refresh, the sample can pick more than one refresh. And the mitigation can refresh only a single victim within a refresh operation. This is probably because of timing constraints. The more important is that sweeping the number of refresh operations and aggressor rows reveal the sampler size, so we could reverse engineer the sampler size. And then we saw that the sampling mechanism is affected by the addresses of aggressor rows. So we found that DDR4 substrate is much more vulnerable than the old DDR3 because we could get bit flips with less than 50k activation per aggressor. So it's possible to overfill the sampler, getting flips, and victim rows may not be properly refreshed by the inhibitor, and this is because we are getting flips. So there are some inhibitor properties, like the inhibitor could be timing based, meaning that it acts on every second, on third or fourth activation on the after the start of the refresh interval, or it could be frequency based, meaning that it acts with a fixed frequency, and the inhibitor could still refresh operation to refresh victim rows. So yeah, we could reverse some DIMMs. We solved that one problem, but yeah, how many DIMMs we could reverse engineer to close the case? So reverse engineering is not scalable. It does not scale. So we decided to go for another approach, and we designed Trespass, and we wrote our paper Trespass in collaboration with the Safari group at ETH of Zurich and Qualcomm. And Trespass is a raw fuzzer, meaning that it's a black box fuzzer, and to scale this approach on many DIMMs and automatically find hammering patterns. So in our hammering pattern, we randomize the number of aggressor rows, meaning that we could hammer 5, 7, 10, 20 aggressor rows, and we could also randomize the location, because we have found that the addresses of the row affect the sampler, meaning that the sampler could it may sample some rows more likely than others based on their address. And we could trigger bit flips or even with Trespass. So we found that target refresh is not secure at 100%. It is discretely effective against state-of-the-art hammering patterns, because we could not find any bit flips with state-of-the-art hammering patterns on our batch of DIMMs. But we found DIMMs that are vulnerable to novel patterns, like the many-sided hammering patterns. The natural question that arises is, what if we combine target refresh with other kind of defenses? So, for example, a double refresh rate. Well, we did it. We still got flips. So, doubling the refresh rate is not a solution. What about ECC? We didn't test ECC combined with target refresh, mainly because we were working on desktop environment. But I believe that combining the many-sided RowHammer with techniques described in the ECC ploit paper, where you can reverse engineering the ECC functions and find bit flips that are not detectable or correctable, and combining these two techniques you can still get flips probably. To summarize, software mitigations have high overhead most of the case. They lack of memory geometry information, while hardware mitigations are they usually have a lower overhead, but they are hardly deployable. We have fragmented solutions. Think about target row refresh, for example, where each vendor implement its own version, and there is missing of a standard. So in conclusion, DDR4 devices are even more vulnerable than previous versions, like DDR3 devices. All major vendors are affected by RowHammer. We found that 90% of the market is affected. And fuzzing can help evaluating the effectiveness of mitigation like target to refresh. However, RowHammer is still a problem after almost 10 years, and we don't have a prompt mitigation available for deployment. So this means that an effort from the security community and the industry is still required. Thank you for the attention.
Thank you. We shall now go to the live Q&A session with them. Just give me a second. There we go. Let me get the Slido on as well. Perfect. Hi Pietro, hi Emanuele. Can you hear me?
Yeah.
Perfect. Thank you for your talk earlier on. It was very, very enlightening. So we've got a few questions. The first one is, how much hardware engineering knowledge is required to research about RowHammer attack?
Do you want to take it, Emanuele?
Of course. Before this question, I have a quick note. So we noticed a mistake on the slides. When I was talking about the inhibitor that could be time-based or frequency-based, I actually meant the sampler. So it's the sampler that could be time-based or frequency-based. Apart from that, about the questions, so of course you need some knowledge about the DRAM technology, so about the DRAM architectures, and yeah, it's really hard to define the actual knowledge you need in this field, because you are doing research. So it's always good to have general knowledge about programming, but about also DRAM architecture and engineers in general. So yeah, do you want to add something, Pietro?
Is there a certain programming language that is more distinct to hardware engineering?
We could do the trespass in C, but you may do it also in C++ or other languages. So a language that allows you to have enough control over the addresses you are targeting. It's enough, I guess.
Yeah, so I think, well, the hardware part, like having hardware knowledge, I think it's useful. For instance, it was useful for us to build a trespass and to do the reverse engineering, but also none of us has actually a hardware background. So we're both coming from a computer science background. And I think it's like it helps, but it's not mandatory. For the exploitation side, not useful at all. I mean, you don't really need to know how you trigger the bit flips. It's mostly to understand, like, for instance, in this case with DDR4, we needed to understand how to get there. Once you know how to get there, you just use any pattern. You can just trigger a bit flips, and that's fine for exploitation. From the programming language, I think it's, yeah, it doesn't really matter. I mean, like, there were exploits even in JavaScript, so, like, I don't think there is anything higher level than that. So, I mean, once you know how these attacks that you build translate to memory accesses, you can do it basically with every language. clearly for a starting point, probably it's better to use something like C or any programming language where you can build, like when you have more control over the memory, as Emanuele said.
Right, wonderful. We've got another question. In your opinion, what sort of software mitigation is most relevant when hardware mitigation is not available?
Well, my idea is that targeted refresh is not so bad in the end because it can really mitigate the state-of-the-art RowHammer attacks. I mean, it is not secure at 100%, but it's an improvement, and I think in the future we will see more and more mitigations implemented directly in the RAM without any support of the system, for example, by the memory controller side. So yeah, maybe target refresh in combination with ECC it's the best solution for now. What do you think, Pietro?
I think, yeah, it really depends on the support that the machine has. So as Emanuele was saying, like target refresh, it's quite decent considering like the amount of effort you need to trigger B flips. I think like a possible, like an interesting solution, which is a bit less demanding in the sense of requirements of the systems, is Para, which is still, I mean, these are they're like in between hardware and software because they're still implemented like at the CPU side. But for instance, like Para was introduced in some laptops via BIOS updates, and you just basically introduce some extra refreshes, and I think that's pretty good because it doesn't require any support basically from the DRAM device. It's just the CPU side, and it just does extra activations, and depending on the probability you set, you get more and or less security. On software side, I don't really think there is much you can do. I mean, like you could design some I don't know, like a specific mitigation for specific use cases. So you want to prevent the exploitability of specific bit flips in the browser, then you can target it directly on the browser itself by doing something with pointers, like trying to avoid like the possibility to corrupt pointers or something like that, which is something like what they did for Spectrum Meltdown now. But I don't see it like in software itself to be a possible solution for RowHammer. So yeah, I think it's like probably Para. It would be my best bet for something that doesn't require support.
Yeah, in terms of security, I think I agree. I was more thinking about DRAM mitigations, but if you think at mitigation that you can use with the memory controller support, Para it's the best solution also for me.
Okay, thank you. And we have one final question for your talk. From an offensive security perspective, what upcoming DRAM technology are you most excited with and why?
Well, of course, we would like to experiment more with the DDR5 DRAMs coming soon, I hope, because we actually don't know if we will be deployed with some RowHammer mitigations or the same situation that we have seen with DDR4 will be repeated. So yeah, I think that the DDR5 devices are the most
I agree.
Waiting for them.
I agree. DDR5 is probably the most interesting bit now because of the trend that Emanuele was talking about also during the talk, that DDR3 was in its own like less vulnerable than DDR4 because it had like less cells inside the memory. DDR5 is going to be even more packed, so most likely the substrate is going to be more vulnerable. So yeah, that's quite interesting. Another technology I think it could be interesting to look at is I think it's called the PIM, which is like a memory with also like a in-memory computation capabilities. So it has some microcontroller on the DRAM itself to perform computations, and I think also that one could be an interesting target to look at also for defensive side maybe. Yeah, that I really didn't think about. Like I think DDR5 at the moment is the most logical step to look into just
DDR3, DDR4, DDR5 is coming. LPDDR5 is already out. I discovered last week, so it's something that it's worth looking into, I think.
All right, wonderful. And with that, I think that comes to the end of this talk. Thank you so much, Emanuele, Pietro, for your talk. I hope everyone had fun. I hope you had fun. Our next talk will be at 4 p.m. Singapore time. That is in 10 minutes. It would be titled Zen, a complex campaign of harmful Android apps by Łukasz Siewierski. We shall see you then. Stay tuned.
Thanks.
Hello and welcome back to the 6th talk of HITB Lockdown002 on the first day. Up next, we have a talk by Łukasz entitled Zen, a complex campaign of harmful Android apps. A quick bio of Łukasz. Łukasz is a reverse engineer on the Android security team at Google, where he takes apart malware and figures out how to stop it from working. Previously, he was taking apart security incidents at the Polish domain registry, figuring out how to prevent them from happening in the future. Łukasz likes sharing his knowledge by presenting at conferences such as Kaspersky's SAS, Virus Bulletin, or RSA Conference. Without further ado, before we start, Łukasz will be on the Discord channel and will not be taking questions live. So if you have a question at any point of time, do feel free to post it on the Discord channel and you should get your answer straight away from him. And now, without further ado, let me start his video. Have fun.
Welcome to my presentation about the Zen, a complex campaign of harmful Android apps. If you consider all the talks about malware that you have seen, there's probably a large percentage that deals with a specific malware family, not necessarily a set of apps that are coming from the same author. This is slightly different. And what started this investigation is I found an app which had an unusual property. This property will be mentioned later on, but this app led me to find a whole portfolio of apps that were developed by the same author, and this talk will guide you through that portfolio. We believe that that these apps were written by the same author or the same group of authors, and it contains repackaged apps with a custom advertisement SDK. It contains click fraud apps that root your phone in order to create fake Google accounts, and apps that are obfuscated and modify the system in some way. Okay, let's start. So first one, as I mentioned, is the custom ad SDK. And what is a custom advertisement SDK? You can think of it like a proxy server for the apps. So for the ads. So what it starts with is you have an app with an ad SDK, and this ad SDK is requesting an ad from the command and control server, and the command and control server gets the ad link from the real advertising network. It downloads the ad, and then it returns the link to the downloaded source, to the downloaded resource. That way you have a proxy to all the real advertising networks, and when you have a proxy to all the real advertising networks, what you end up with is you end up hiding them from the actual app. So when you are reverse engineering an app and trying to find out which advertising network it's using due to this proxy infrastructure, that won't be possible. And it also can be used to hide the ad network abuse. So when you're reverse engineering the app and it's doing some kind of an ad fraud, what happens is you don't really know which ad network is being abused by this app because it's hidden behind the proxy itself. This is a fairly easy concept, and the apps that use this SDK can be divided into two groups. So first one is what you can see in the screenshot here. It's the actual game that's on top, and when you click on play, you will go to the game and have the same experience as you would if you were playing a game. And what you see below the play button are ads. And these ads are coming from the ad SDK. You can see that the user is maybe inclined to click on the ads instead of clicking on the play button. And when that happens, the ads are from the CNC. But when the user clicks on the play button, they will get the same experience because, again, the app is repackaged. It's the same popular app that the user wanted to use, just in a different form with additional ads. And the other kind of apps that use this as ad SDK is it's not real apps, but apps based on the real app, and they mimic the popular apps, but they do not provide the same functionality for the user. So they only pretend to be the app that user wants, but instead they will just show ads to you. And that may not be a great user experience, obviously, because user only gets to see the ads that are coming from the CNC. So this is fairly simple. And as I said, this custom advertisement proxy SDK is not malicious in itself, and those proxies don't necessarily have to be malicious, but they allow the attacker to hide the real ad network. So this is one of the simplest apps in this malware author portfolio. Now we can move on to slightly more complex apps that are doing some kind of ad fraud, and this is click fraud. So click fraud in general is defined as just clicking on an ad or generating an ad click instead of the user clicking on the ad. It's something else that's clicking on the ad automatically. This can be done on Android in 3 different ways. This can be done purely in JavaScript. So you load a website and that website contains a JavaScript, and that JavaScript clicks on an ad automatically. It's nothing related to Android. It just happens that the website that's loaded is clicking on the ads. It can also be done using Android API to simulate the user click. And when the user click is simulated, the ad is clicked, and it's slightly harder for the ad network to detect because the JavaScript part is obviously loaded through a website, so it's a part of the website, but here the ad network thinks it's coming from the Android API. It can also be a mix of both, and it's a mix of both when the app is exposing a JavaScript interface. JavaScript interface is a way for a website to use JavaScript to call a Java method that's implemented in the app itself. So the app exposes a JavaScript interface. The JavaScript code calls a method that's exposed using the JavaScript interface, and then a Java code is executed on the Android. And that Java code can, for example, simulate a click on an ad. And that way the attacker gets some information from the website, and based on that information, they can click on an ad. And you can see that apps that are click fraud are blocked by Play Protect. So what you can see in the screenshot is when the app that was a click fraud app got blocked by Play Protect. And you can also see that there's a short explanation of the type of malware that was blocked. So it says this app can simulate a tap on your screen's content, such as an ad in the background, right? So during the install process, when you see that that warning, you will get some information about the app, and you can interrupt the installation process and not install the app. The way this click fraud was done in this particular set of apps that come from the same author is through a rather large JSON object. So the app contacts the CNC server, it gets back a JSON object with a rather large list of different key value pairs. And the list contains the strings that will be matched against the HTML of the website. So what you can see in the screenshot here is you can see the keyword, and the keyword is something that will be matched against the HTML. And then you can see the JS key, and JS is the JavaScript snippet that will be executed whenever a keyword is found on the HTML website. So the goal of the app is to look through the website and then execute JavaScript if something happens. And you can see the first example here. It looks for an A element that is of a class show height btn next. And that keyword, if it's found, then a JavaScript will be executed, and that JavaScript looks basically for the same element and then clicks on it. That way the app can ensure that the keyword was found and that the element is on the website, and it can execute the JavaScript and not worry about the element not being found, because it's obviously there. When I said that there is a rather large list, I also mentioned at the beginning of the talk that I found an app that had a really weird property. And that weird property was the CNC response. And the CNC response was unusually large, which in some cases may mean that the app is downloading an additional code from the server or an additional app from the server and is doing something with it. But in this case, the thing that it downloaded from the CNC was this list, and this list was quite large. So what you can see here in the screenshot on the right hand side is that list. It's actually 1/3 of that list, and you probably cannot see the characters because they are so small, but it's still 1/3 of the list. So if I copied it 3 times, it would take the whole slide and you couldn't see anything. And that's 287 kilobytes of click-through commands. So that's 287,000 characters of click-through commands that are being transported from the CNC or received from the CNC. And this means that the author doesn't necessarily care about accuracy or compactness, but it works. It just needs a bit more of the processing time to go through the whole list and find the elements that match and then click on it. So, as I mentioned, applications that perform click fraud are classified as malicious applications, and you will see the Google Play Protect warning if the app is classified as a potentially harmful application, and then your install process will be interrupted, or you will be asked to uninstall the app from your phone. Okay, let's move up the technical complexity of the apps. So I mentioned the very simple ad SDK network, and then I mentioned the click fraud. Now we are going to routing and account creation. So the way this app routes the phone is it uses an API to connect to a server and then downloads something they call solution. Solution in this case is an exploit that is downloaded from the CNC. And the app sends the device info to the CNC, and then CNC decides which solutions or exploits will be downloaded and will work on this particular device. So what happens here is that the exploits that are on the CNC are protected in a way from the reverse engineers, because you have to know which device you want to exploit, and then you send that information to the CNC and it chooses the exploit for you. So you never know which exploits are available on the CNC and which devices can be targeted. Once you get this solution, there is a call to set crack type. This is just a way to define the interface between the solution and the app. So there is some common interface between them so that the app knows how to call the exploit or the solution. And it gets the file name, and if it's successful, then it will upload the information that is successful back to the CNC. So when the exploit works, it has the root privilege. And then what it does with the root privilege is it enables accessibility services. So accessibility services are these services on Android that allow, for example, people that have their eyesight impaired to be able to use the phone in a more accessible way using, for example, a screen reader. So obviously the app that has accessibility services has some a bit more privileged access to the device. For example, it can read the screen in order to read the screen. So this app, if it successfully rooted the phone, it already has the same privileges, but it uses accessibility services to have some kind of an API. So it doesn't necessarily elevate the privilege because it already has the root account. And you can see that first thing it does, it gets the list of enabled accessibility services, then it adds its own accessibility service and saves it as enabled accessibility services, and then sets accessibility enabled to 1. So what this does is it just adds an element to the list for the user. So user is not aware of that. If user was aware of that and it went through the regular process of enabling the accessibility service, user would see something like this. And this is actually from the app itself, from that app that requests the accessibility services after rooting your phone. But the user again won't see it because the app does it for them. You can see that the screenshot here asks for a privilege to observe user actions and retrieve window content. So again, it will be able to read the screen and observe some actions. Okay, what the accessibility is used for is it's used to create fake Google accounts using the account creation wizard. So these are some screenshots from the account creation wizard. You can see that there's an entry verification code, basic information about your birthday and gender, and how you'll sign into your account, so your username. And you can see the code of the app below, and that's the title contains enter the code, or the title contains basic information or something like that, and based on the title of the screen, different action will be performed. One of the titles that you can see is base64 encoded, and this is the only base64 encoded or the only obfuscated string I saw in the whole app. I don't know why the author chose to obfuscate that. It also correlates with the fact that there's apostrophe in the name. Maybe that's related, or maybe they were trying to circumvent some kind of an NAV fingerprinting or something like that. But this is the only string that's obfuscated, even if it's just base64. So now it has access to this account creation wizard, but it needs more information in order to create the account. And this information is supplied by the CNC. So first thing is the phone number, and the phone number is sent from the CNC. So the app contacts the CNC, gets the phone number, but also in order to verify the phone number, it has to get the one-time password. The one-time password is sent using a text message. So the app needs to contact the CNC again to see the text message. And this is what you can see is being done here. First, it got the phone number, and then it contacts the CNC with that phone number that it used for verification and says, hey, did you see any text messages coming to that phone number? And if the CNC saw some text messages, it responds with the text message content, and this text message content is processed here. As you can see, the response starts with MSG ampersand, and then it looks for is your Google. So it looks for the verification code, it parses the verification code and gives it back to the account creation wizard. As I mentioned, it all started with routing. So the first step is to find a solution, what they call, or an exploit. And it's very hard to find a reliable exploit for newer Android devices that works across all of the Android devices. So the risk of getting infected is slightly or significantly lowered on newer Android devices. Now, let's move to code injection and obfuscation. This is a even more technically complex part of the app, and this is something that app can do because the app was able to root the phone. So when you have root, you will have the ability to ptrace into other apps. And this is the diagram for the code injection. So it starts with the source application, which is on top in light gray, and the target application is below in the dark gray. The source application, the way we will read this diagram is from the left-hand corner, top corner, and then we will move down in the diagram. So you have the source process. It calls the inject remote process method from the LMT inject framework. And the parameters to that method are the target process ID, the one that we want to inject the code to, the name of the file where we can find the code that will be injected, and the method that we will inject to the target process. So what you can see here is that it p-traces into the target process. It can do that because it's rooted. The phone is rooted and it has the root privilege. And then it will move the program counter to some other place. And in order to do that, it has to map memory in the target process, just so that it can put the shellcode that would load the inject.so file, and it will start the do stuff method. So in order to do that, it has to find libc. The way it finds libc is by going to /proc/process_id/maps of the target process. And that is where it will find the mapping of libc in the target process. And then it can use offsets from its own mapping of libc to find where mmap function is. And it can allocate the memory in the target process. And in the allocated memory, it will just have the code to dlopen inject.so file, and then call the method, or find the method and call it. And again, dlopen and dlsim are found the same way that mmap is, by looking at the mapping of libc and then looking for the specific offset. So this is how it can execute code and do stuff in inject.so. But this whole complex process of injecting the code into the target application is used for a very specific purpose in this case. And this specific purpose is to get the CAPTCHA image. So during the whole account creation process, it may happen that the user will be asked to solve CAPTCHA. And the way it's handled by this particular malware is it extracts the CAPTCHA image. For that, it has to inject code into the account creation wizard. And it will extract the image, send it to the server, and then the server will respond with the CAPTCHA solution. I don't know whether it's done automatically or manually, or in what way the server solves the CAPTCHA, but it just sends the whole image and gets the code back. So what you can see here is basically it. It gets the CAPTCHA image view element, UI element. This contains the CAPTCHA image, and then it requests the code that this decrypted to. So it encodes the image using base 64, sends it in a JSON object, gets the response with code, enters the code into the account creation process or account creation wizard. It also uses that code to hook internal methods. And the way this is done is by looking at the methods that may interrupt the account creation process. So for example, one of such methods would be reboot. If the phone is requested to reboot, for example, by the user, this may interrupt the account creation process. So what this malware does, it creates a hook in the Power Manager service reboot method. And that hook doesn't do anything apart from returning 0. So it effectively stops the reboot. And you can see here something called dexposed is used, is used, and it can only be used because the phone is rooted, right? So then it finds the find and hook method for reboot in the Power Manager service. So you can see that there's a method called before hooked method. This will be executed before the reboot is called. And as I said, the only thing it does is returns the value, effectively stopping the reboot because the value is already returned, so the method doesn't have to run, and the phone doesn't have to be rebooted. It also hooks a bit more. So it also hooks the a method that is used to process some keys. You can see that key power, menu search, volume up and volume down, and volume mute are being hooked. And instead of processing the event of the key being pressed, it will just return the value 0. So even if you click on the power button, you probably won't see the reboot option. And if you want to reboot your phone, it's also hooked, so you won't be able to reboot your phone. So I said that code injection was possible because the phone is rooted, but again, you have to gain root disable SLinux, and on newer Android versions, the /proc file system is more locked down, so you cannot look into maps to find out where the libc is, because you cannot access the proc file system for a different process ID and find the location of libc. So this framework will fail on the newer Android versions. And the DES is used here to obfuscate the sample. So this is pretty interesting. The app contains an asset file, and that asset file is in the X directory, and its name is a number. And this number in the file name is used as a string, as a key to the DES. It's not used as a number key, but it's used as a string key, and then it's decrypted, and the code is loaded and the code is executed. So some of the versions implement this kind of obfuscation. So we know how the code is obfuscated, what it does, how it creates the account, how it deals with the CAPTCHA images, and all of that. So let's move on to the persistence. And persistence is just a way for the system to create to hold on to the whole Android system. So it's a way for the malware to persist. The first method is it writes to install-recovery.sh. Install-recovery.sh is this script that is called during the boot process by init-d. And this install-recovery.sh contains lines of script. And one of the lines that is added by the malware is just command to execute the daemon, the ZLT daemon, which makes sure that the app is running, so the app will run during the boot process. Another way of achieving persistence is by installing apps in /system. So installing the apps in /system allows the app to make it a bit harder for the user to disable it. If app is installed in /system, the user can disable the app, but the file will stay on the system partition. And this is due to the way that verified boot works. The verified boot feature calculates hashes from the system partition, and these hashes have to be the same as the hashes that were either during the update or in the factory when the system image was created. So that makes sure that the system partition was tempered, and if the app from the system partition was deleted, then the hash would obviously be different. So that's why the apps on the system partition are not deleted, they are disabled. And what this app does is it remounts the system partition as read-write, because the system partition is read-only, and then copies itself to the priv app directory where some of the pre-installed apps live. And once it's copied there, it's viewed as a system app, so it can still be disabled, but it cannot be as easily removed from the system. But the only difference between disabled and removed is that the file is there, but the app is still not running. Third method of persistent is by adding code to the activity class. And now the activity class is one of the classes in the Android framework, so it's not so easy to modify. The way this malware modifies it checks whether the build fingerprint is the one it wants and one it knows about. And then it swaps the whole framework.jar file. This is a slightly dangerous operation because if you don't have the right framework.jar file for the right device, what will happen is the device can be effectively bricked in a way. So the malware has to first check whether it is on a correct device, and then it can swap the framework.jar. And the only thing it does is it connects back to the server saying that I'm still here. So it just sends back a ping. And the activity class itself is a UI element on Android. So to put things very simply, anytime you interact with the UI, it can be an activity class. So if you open a new app, you open a new activity, this statistics method will be called if your phone is infected with this particular malware, and it will connect back to the server. And finally, the fourth method is by injecting into the system server process. So the system server process is something that just runs in the background constantly in Android. And because it runs in the background constantly in Android, it will persist until the reboot. So if you inject code into there, your code will run until the reboot. So the malware injects the code using basically the same framework that I described. And then it also checks whether the tracer PID is there. And the tracer PID is the process ID of the app that did the ptrace. So you saw in the previous slides that there is a source app that ptraces into the target app. And when it does that, the tracer process ID will be altered or will appear in the proc file system. So the app can check whether the injection was successful by looking at the system server tracer process ID. And if it's there, it doesn't have to inject the code again, and it can report back that the injection was successful. So I mentioned 4 methods. This is a small summary. 3 of them are protected by verified boot. So I said about installing the app in the /system directory. Same applies to install recovery. Install recovery is also part of the system image. So if it's altered by adding additional line of shell script, it will be detected by verified boot, and the boot process will be stopped because the system partition is different. Swapping the framework jar, same story. Android framework is part of the system partition, so verified boot will detect any changes to framework.jar. And when you inject code into the system server process, you're injecting code into memory. So obviously verified boot doesn't play a role here, but it won't survive the reboot. So all 4 combined don't really provide a good persistence against new Android versions. And one other thing I want to mention is the actual timeline of the apps. So the way I presented the apps here is by starting with a very simple app that had ad SDK, additional ads in the repackaged apps, or pretended to be other apps but with ads in it. Then we went to click fraud, then we went to routing, then we went to account creation, code injection, and all that technically complex stuff. So I kind of lied to you, and the way I lied to you is I presented them in the order of increasing technical difficulty, but this is not the same order as the timeline. The apps were created in a different order, and this order supports what we saw, and that is that the malware developers are moving away from routing exploits, because routing exploits are harder to find. So the first sample that we saw was using dynamic code loading. So it was very hard to definitely say what it was doing. It was definitely displaying ads, but it also downloaded additional code from the CNC, so it's possible that it was doing more than that. Then we saw the routing exploits. It was less advanced than what we saw here. Obviously, it developed over time, but it tried to get root privileges. Then we saw the click fraud. So you can imagine that after the unsuccessful rooting attempts, the author moved on to click fraud with the enormous JSON that attempted to click on ads. And then they introduced the DES obfuscation that I was talking about with the asset file. So the timeline is slightly different than what I presented here, but I think that presenting it in a order of technical difficulty provides a more useful presentation. So, as I mentioned, the author had to pivot from rooting Trojans because it's harder to exploit an Android device. So they moved on to something different, like click fraud, even though it's slightly less advanced than the rooting Trojan. Okay, so let's sum up what I was talking about here. First, the verified boot makes sure that the system partition is not altered, which prevents the persistence part. Rooting is harder, more expensive, sometimes it's not even possible, which prevents the app from rooting the device, which prevents it from enabling the accessibility and creating fake Google accounts. Code injection open source frameworks like the one I described here are broken since Android Nougat because proc is more locked down, so you cannot so easily go to maps and by going to maps see where the libc lives, and you cannot so easily navigate the memory of the other process. We are also actively looking to better detect click fraud apps. I showed you the screenshot that will be shown to some users if the app is deemed to be a click fraud. We are also looking at root enabling app droppers. So again, something that roots the phone and then drops the additional apps and makes them slightly more persistent or something like that. We are looking into it and making sure that it won't happen anymore, even though the exploits aren't so widely available. So, summary of the whole presentation is that I wanted to present something slightly different than what you will usually see. So instead of focusing on one malware family, I presented you a portfolio of different malware families that are linked by the same author or the group of authors. Android malware families usually tell only one side of the story. And that means that eradicating one malware family just may mean that the author will move to a different malware family. It doesn't necessarily mean that the author doesn't come back with something else. So we have to take a step back and not only figure out what the malware family is doing, but maybe what the author goals are, what the author may do in the future in order to create more malware and monetize the infections in a more profitable way if one avenue of achieving that profit is closed. Okay, and obviously attribution requires different tools. So not only we have to take a step back, but we also have to change our mindset in order to make sure that we do attribution correctly. That is all. Thank you. I will be available on the Discord channel where you can ask questions. If you don't manage to ask questions on the Discord channel, you can also ask me on my Twitter account. And thank you again. That is all.
Thank you, Łukasz. Like he mentioned, he will be on Discord channel, so you can ask any of your questions over there. Coming up next would be our final talk of the day, FIDLing with Decompilers, by Carlos Garcia, as well as Ryan Warnes. That talk is scheduled to start at 5 p.m. Singapore time, which is in about 20 odd minutes. Even though this is the final track for final talk for track 1, track 2 will be going on till 11 p.m. Singapore time. So head on over there once you're done with track 1 and watch more goodness. We'll see you then at 20 minutes from now. Hello and welcome back to track 1 of HITB Lockdown002. This would be the last talk of the day for this track, but don't worry, we have more talks happening in track 2. For now, we have Ryan Wons and Carlos Garcia Prado talking about fiddling with decompilers. A brief introduction. Carlos studied particle physics back when computers were not cool yet. After realizing he missed out, he started teaching himself and has been in security for about 10 years now. He has worked mostly in the offensive roles in several companies, from small consulting firms to larger ones, lately involved in corporate security at Siemens and redacted at the Huawei European Research Center. Currently, he is the staff vulnerability engineer in the FLAIR team of FireEye, where he does vulnerability research, tool development, and malware analysis. His interests are IDA, Windows, Python, WinDebug, popping up after a fuzzing campaign. Ryan Wons is staff reverse engineer in FireEye's FLAIR. In his current role, he acts as a reverse engineer performing malware analysis and a security researcher specializing in vulnerability analysis and payload development in support of FireEye's Red team. Prior to joining FLAIR, he worked for the DoD, specializing in Windows internals, capability development, vulnerability research, and low-level software engineering. This talk is a pre-recorded video, and both of them will be on Discord channel answering any questions you have. There will not be a live Q&A session, but they will be on the Discord channel. So if you do have any questions at any point throughout the talk, please go ahead and put it in the Discord channel. Without further ado, let me start their talk.
So, well, hello, we are Ryan Wons and Carlos Garcia Prado talking to you from Singapore. Oh, wait, no, we are at home, but anyway, this is Hack in the Box, and we're going to talk to you about fiddling with decompilers. So very briefly, the agenda, we're going to talk about, how to do source code analysis without the source code. Then we're going to see how, decompilers are hard. Afterwards, we're going to see that IDA is hard as well. We are going to introduce our solution to this problem, namely a library for interacting with a hex-raised decompiler, making your life hopefully easier, called FIDL. And at the end, we're going to see how you would be able to do this at the scale. We'll be reversing and decompiling at scale. So yeah, who is this? Ryan?
Yeah, my name is Ryan Wons. I've run the gambit in terms of sort of low-level reverse engineering stuff. So I've done, malware analysis, vulnerability research, worked on Windows, worked on Android. I've kind of, done just about everything. So.
And I am Carlos Garcia Prado, also go by Carl OS. It's pretty easy to distinguish us because I'm the one with the accent. I actually did not study computer science. The computer science guy is Ryan. Did physics a long time ago in another life. I really like IDA, Python, and Windows stuff in general. Love to automate stuff, and that's why we are here. And I've been like around 10 years in offensive security roles, different ones. Before we start, we would like to give a shout out to some other people doing like what we think is very interesting work in the compilation topics. And yeah, definitely Patois, or I don't really know how to pronounce that name. Everything from this guy, it's totally worth it. It has like extremely good IDA Python plugins, so go check it out. And of course, this tool is very useful as well. We use it all the time.
So yeah, kind of to set the stage for what we're talking about and where we think FIDL slots into the binary analysis, reverse engineering, VR process. Usually what ends up happening when you're going through and doing something like VR is you'll have your fuzzer running in the background, hammering away to try to do code coverage and all those kind of like dynamic instrumentation metrics. And then independently of that, you want to be looking at the code base sort of yourself, right? Because that lets you do things like, maybe I want to drill down in a particular area, or maybe I have some sort of data definition wrong in kind of my fuzz case, and it helps you sort of independently and in parallel build out these different like use cases and places you want to look and things you want to do. So when we're talking about source code analysis, it's both looking for bugs, but also it gives us a lot of insight because we have things like what functions call what functions and sort of some code flow structures there. We also have this idea of we know the data structures, we know which structures are meant to work in tangent together. If there's any things like structures and structures or reference counting or any kind of things that would be prone to those logic errors, basically by looking at our source code, we can sort of understand the code base as a whole. And that's more or less a different mechanic that we can both use to find bugs while we're fuzzing, and then also take that information and feed it back into our fuzzing framework with sort of some, increased granularity. So we're writing more accurate fuzz cases, and we're ensuring that we're touching more pieces of the code that way. And this holds true for whether you're doing VR or just kind of general purpose reverse engineering too. So when we talk about the problem that we're trying to solve here, when you're doing some kind of VR project on something that's closed source and you don't have the source code to rely on, your workflow is ideally more or less the same. You have your fuzzer running on one side, you're sitting there crawling through the binary. Oh, I found something interesting. Is that a bug, or can I use that to inform my fuzzer on the back end? But the problem is when we don't have source, it probably makes sense to most people, but we also lose all of the information that we would normally be looking for when we're doing our manual analysis process. So a lot of that things like code flow might be harder to track and harder to understand, or even we have these sort of sophisticated disassemblers nowadays, but there's no guarantee that whatever heuristics they're using to massage and manipulate the binary will accurately represent things like how big are structures, which structures are meant to interact together, or what kind of data types do structure members have. So all that information basically gets lost to us. And when you're talking about code flow and you're talking about vulnerability research in particular, C++ is a classical example where, because you have a bunch of objects in memory all passing different structures around and calling function pointers in and out of each other, tracking all of the code paths that a binary can possibly take gets really complicated really fast. And by nature of how disassemblers work, you lose things like cross references usually for B table functions and some of that kind of information that's super useful to us when we're trying to understand how a binary works and how to, by extension, fuzz it and attack it for vulnerabilities. So fundamentally, we lose all this information that we would be relying on because compilation is a lossy process. And really what I mean by that is that when a developer builds source code or pushes it through a compiler or some kind of build framework, the compiler is only beholden to make sure that the thing that runs in the final binary is what we intended to write as an author. But it's not beholden to the how it gets from point A to point B. So things like structure definitions could be moved around. There are optimizations in place that might change how code works or how functions are compiled or how it looks or how it runs. Then on top of that, another way to think of it is when you compile, you have basically everything you would have if we were looking at it from like a source code perspective. So things like header files, type defs, function definitions, structure definitions. The compiler has all of that information and then basically throws away the stuff that's unnecessary for execution. So the compiler doesn't have any need to know how structure A is defined as long as it knows where the data is supposed to go sort of in relation to everything else that's using that structure. So what ends up happening is we have all this information in our source code, but the compiler only needs like 60% of it. And that's before we even start to talk about things like function names, local variable types, all the stuff that would normally be in like a PDB file, for example. We lose all of that. So when we're trying to keep our workflow the same for doing vulnerability research or some kind of binary analysis, it would be super helpful if we had some tools to essentially wrangle that compiled binary and recover or take a best guess at recovering some of that information that gets lost in the compilation process. So that's really what we're talking about here, and that's really where you'll see our tool comes into play, because normally what will happen is we have tools already written for us called decompilers, which do some of this for us, but we'll see where that kind of breaks down and where it becomes kind of complicated for us to use out of the box. So just to give you a general idea, when we're talking about a decompiler, we just kind of walked you through the base case where I said the compiler has all the information when it's building a program and it throws some of it away. But you can rely on things, if you want to reverse that process, you can rely on things like common patterns that are seen in compiled code, or sort of behavioral things that you would expect, and you can kind of run this heuristic over it to build a more or less accurate representation of how these things work. So just as kind of a quick and dirty example, when you're going through and these decompilers are trying to lift up all this logic out of a compiled binary, you'll have your assembly code sort of at the base layer, and they'll all have disassemblers and they'll understand how to interpret these instructions. From there, you can track things like, is this a stack variable or an allocated buffer or some other kind of data structure, and you can convert these simple, one-line instructions into kind of a higher level representation. So, in this example, EBX is some kind of maybe function pointer or structure pointer rather, and we can convert sort of raw assembly into kind of a more logical representation. And then from here, there's not really a silver bullet or a quick answer. It's basically the dragons of optimization. But what it does is, once we have this higher level representation of what all this code is doing, from there, those are the building blocks that we can use to really start to make some guesses and assumptions and deductions about what a function is supposed to do. So once we have that sort of IL, or that intermediate level representation, we can take that and build that into what's shown here, which is an abstract syntax tree, where essentially you've mapped from sort of raw assembly to some kind of thing that more or less looks like a logic tree. And that logic tree lets us start to tease out things like conditional statements or switch statements or loops or any of that kind of stuff that you would see in your source code. So as the result of all of this, once we've done our sort of fancy optimization, we get something that looks similar to source code. There's no guarantee that it's exactly what we would have expected when there's no guarantee it's exactly what we wrote when we were compiling the code, but it's a pretty close approximation. And this is all kind of a simple example, but obviously as things get more complicated, as you have more functions, as you have more structures, as you have more cross references, this all blows up kind of exponentially. But that's kind of the idea for decompilers, is we want to step by step, piecewise convert from a higher level, from a lower level representation to something that looks like source code, and we can work with that because it's a lot easier for us to process the box on the left and a bunch of boxes shown on the right. And then the AST, if you've ever looked at IDA's existing API, this is sort of their core mechanic. This is their favorite thing that they like to use. This is what their API is built on, is kind of iterating over this AST in order to make some kind of scripting framework around it. So in general, there is a lot of work shown on the decompiler. It's not a sort of new field of study. There's lots of work. There's lots of different decompilers out there nowadays. So if you want to dig into it and get a little more detail about what some of those dragons I talked about on the last slide look like, here's just a simple LLVM doc. You can go ahead and dig into that at your heart's content. But for us, for this talk, luckily what we're going to be able to rely on is that a lot of this fancy work, a lot of this magic, a lot of this computer science is already done for us with tools like IDA on the left or Ghidra on the right, where they've already kind of gone through that process of taking assembly code, lifting it into a higher level representation, and then they produce the end result, which is shown on the screen here, which looks a lot like C code, maybe not very pretty C code, but pretty enough for us to kind of process and understand. And for now, it's enough to say that there is an AST that's kind of backing what's shown on the screen here. So if I want to script against this output, I'm not scripting against like text or something like that. I'm scripting against whatever the decompiler's representation of a function is. And where it really starts to break down from a binary analysis process, which Carlos is going to go into in a couple seconds, is while things like Ghidra and IDA are very sophisticated and they've done a lot of work in sort of that language lifting component of it, by nature of being very complicated, they have kind of a very complicated API. So when we're trying to do things like write scripts against it to do binary processing, there's a pretty steep learning curve. And in a lot of situations, it's really hard to massage the existing default API into doing, what we need it to do from a binary analysis perspective.
So yeah, the reason actually behind the bad joke saying like ain't nobody got time for tap is that the decompiler in IDA, let's talk just about IDA and focus on that. It's very good, it's very mature, but it has been designed apparently to be used like kind of interactively. You're in front of your function, you're doing your analysis, you press tab, and then you switch to decompile code. And and life is better, but still you're just looking at one single function, then you move to another one and you do the same. So we would like to have something that actually is more programmatically and that we can tackle like many different functions inside the binary, inside a script or a program, not necessarily having to be in front of it. So yeah, there was many shortcomings for the way that we work reversing binaries. So that's why we brought here our own solution that it's called FIDL. You have it in there in github.com if you want to go for it. I will show you links later. And we kind of defined this thing as a sane API for IDA Pro's decompiler because the raw API, it was like too complicated for us. It was, I had like a very, very steep learning curve. So just let me mention that when we put this thing out there, I tweeted, whoa, finally we have something that makes the IDA decompiler API usable. As you may have noticed, I'm not exactly an English native speaker, so there was like let's say, a poor choice of words. So we got this answer from Ilfak. In case somebody has been living under a rock, Ilfak is the creator of IDA Pro. So yeah, there were some people like piling on and saying like this is very inflammatory. But at the end of the day, Ilfak said, "Oh wow, I like this. This is wonderful." So we gained his love again. So everything is cool. This is, so to speak, Ilfak approved. So yeah, but let's talk a little bit about the internals of FIDL. So one thing that you're going to be using all the time if you choose to use FIDL is this thing called control flowinator. We know it's a dumb name. We like dumb names. This essentially is kind of a data structure representing a single function. And you can think about it, it's like a mix between a control flow graph and this decompilation output that we showed you before. And in order to understand this thing better, imagine that you have like a control flow graph, like the one you have in assembly mode. But now every node is actually a high-level code artifact. It's, for example, like an if statement or an assignment, or, it's like a function call or whatever. So it looks, when you are debugging it and look at it as something similar to this. So essentially, if you have been using IDA, you are used to this representation that is a control flow graph with just a very, you're deep into the binary, you're just looking at the assembly instructions, or if you're lucky enough or to have the decompiler plugin, then you are used to this. This is exactly the decompile code of this assembly on the left. So now what you have with FIDL is something in between those. So there's this control flowinator that we show you, in which you have like kind of the best of both worlds. So you still can work with a graph. So if you see, it's like logically very similar to the one that you had at the left. So you can use all those, very juicy algorithms. You can traverse the graph and look for all the paths in between A and B and all those things that are like very natural in order to analyze a binary or looking for something. So it's something like in between those two that you already know. And as an example, look at this node, something that we said before. This is an assignment. That would be, this node would represent actually this line of code. Right now, at the very beginning, it's just like a simple node in a graph, but there is many APIs. FIDL is pretty rich in order to, let's say you want to zoom into this node and then take a look at the details. For example, is the left-hand side, like is there a variable in there? Is the right-hand side a number or whatever it is? So you can do all that. But at the very beginning with the control flow inator that, I repeat, you're going to be using all the time if you script with FIDL, the first thing that you get is kind of a high-level overview of what is going on in this function logic. So yeah, here we just wanted to show you that this really, even if you have a function like this one in the left, one of those functions that you're reversing are like, oh no, I don't wanna mess with that. And the thing that you see in the middle would be like the control flow inator associated to that one, and on the right we're just showing you, like it's zooming in there so that you have an idea of how complex this thing is. So this thing it scales like very, very well. And by the way, we're showing you those graphs all the time. And you can generate those things because those are produced by FIDL itself when you're debugging. So if you're really deep into FIDL, if you want to contribute, if you want to look at the algorithms and improve them and send us a PR, we would be like very happy. Nothing to complain in there. You have those, let's say, those facilities in order to do some debugging as well. So this is just like a dot generated graph. And yeah, talking about dot, like again, we wanna make clear that this thing is ready for like real life binaries. It's gonna take more or less time, of course. But even if you have a function like this, that is, like it's reverse engineer hell, you can create a control flow inator. This is just just created a control flow inator of this function, and you see in here, I did not display that, but if it's in here, okay, just IDA says like no problem at all. I just created the control flow inator object that must be huge. If I try to display it, dot is gonna crash, at least on my machine, saying that is out of memory. So once again, what we're trying to say in here is this thing is ready for real life binaries. We have been throwing like everything at it, and it works pretty well. And another thing is like we have tried to make this thing kind of batteries included, so kind of the same philosophy behind Python. And when you create a control flow inator for a specific function, by default, it's going to have a lot of very interesting information. For example, it's going to have information about all the function calls inside this function, of course, the local variables, the arguments, and return types, many things that they're accessible to you like very easily. And this is just a code snippet showing you, this is something that you're going to be like doing like all the time. Of course, you're going to be importing FIDL. Then you create a control flow inator that has a couple of parameters. One of them is just one address inside the function that you want to represent or get information from, and the other one, most of the time you're gonna be, it's gonna be good that you set it to false, because then you're gonna get all those goodies. And as I said, you have this object C that is just like the control flow inator, and very quickly you can access them very, let's say, comfortably. You can access all this information that you would suppose it should be easy, to get that, those basics about, I want to know about, in this, as you see in this snippet, I want to know about this specific function. Tell me about all the local variables. Tell me the names, the types. Are they an array or not? Are they like a pointer to some other complex type? All this is encapsulated by FIDL, so you don't have to put a lot of work or almost any work in getting the easiest things. This was one of the design principles. We will try to give you as many things already digested for you, so that you can concentrate on the things that matter, not just being lost in the details. So
yeah, so like Carlos was saying, we've kind of gone through how Fiddle's built in the back end and we'll now show some examples of what it can do, but basically there's kind of like a so what question, why do we bother? Why do we do this? Why is this helpful? And for us, like I said, it's not that existing tools are insufficient. It's more like the questions that I need to ask if I want to run sort of a binary analysis script, over a large section of binaries or a large collection of binaries, right? There's kind of some common things that I'd want to do over and over and over and over again. So, we're from the Flare team. We do a lot of malware analysis, for example. There are certain code patterns that you see in malware, ad nauseum. So it'd be super helpful if we had something to sort of just kind of script against those. And the problem is, because Carlos was saying, essentially a lot of IDA's APIs are meant to kind of work from a workflow where you're in front of a terminal and interacting with a binary, clicking through functions and kind of looking at functions one at a time. We had to spend a lot of time sort of digging down and really understanding what makes it tick when you rename a variable or when you decompile a function or something like that. So a lot of those APIs, it's not that they were inaccessible or anything like that, but sort of the workflow that you need to go through to make modifications and extract data in a way that's very useful is kind of tricky. And if you're not using the AST, it gets even harder because, like I said, a lot of sort of, at least from our perspective, what we found in practice is that a lot of the way the APIs work is they're designed around that AST. And using that as kind of your core data source, which is sort of something not that we wanted to avoid, but for flexibility reasons, we had to dig a little deeper, which meant a lot of DIRs. Is this function right? And this one kind of looks like it, but then you have to call function A, then function B. So we did sort of all that information for you, because the idea is like we want to give you a framework to allow you to focus on sort of the big picture stuff. Like if I just want to say, I want to scan a binary and look for these 5 things, I don't really want to have to worry about reprocessing the AST every time or re-understanding some sort of mechanic or edge case or something like that you ran into once about, an assignment statement or something like that. So we've extracted all of that away. And the result of that is if we have these sort of use cases like this, so as a very simple example, one of the most common things you're going to do, particularly when you're talking about malware analysis, is I want to find all the references to a function and then extract a parameter from it, right? So what we have shown here is, the set dialog item text function call, but, it would also be analogous to if you had a get proc address call, like understanding whatever that string value is in order to extract whatever kind of dynamic function lookup was being done. So if I want to take this example and say I want to find instances of a function call inside of a function, so I want to find references to my set dialog item text A, then I want to grab any argument that is a string, and I want to get that string and print it out, or in some cases you could use it. You could imagine if it's a debug message, you'd be able to log that or put it in a comment or even rename a function sort of around that functionality. So this sort of simple extraction of parameter data is super useful. But where it, again, not where it breaks down, but where it sort of hits the road for us is if I want to do this with IDA's existing API, everything will work fine. But I need to write sort of a class like I have here, which, if you're unfamiliar with IDA's API, essentially this visit expression function that I have defined on line 13 is there to function basically as a callback. So you would say, hey, look at a function, IDA will decompile it, and then IDA has access to its AST, so it'll iterate through the AST for you more or less, and then you'll get this callback as it visits certain nodes or certain expressions depending on how you build your class. And so this is sort of the intended solution when you're talking about IDA's API, because you would basically iterate through the AST, you would look for function calls, which I have shown on line 14, and then once you have an instance of a function call, you can dig down into it. So is the function name set dialog item text A? And then from there, you can go through the parameters. For each parameter, you can check to see if it's a string, and then if it's a string, you can extract it, right? And this is all, it's all well and good. It all works. And once you're familiar with sort of the workflow of it, it's fine. But where it breaks down for us from like a general perspective is it's kind of twofold. One, on line 16, you can see an instance of us taking a node, which is in the I variable for this case. And this concept of I.x and I.y are how you iterate down the tree. And when we're talking about the AST, again, remember, we're saying IDA visits it for you, but there's some instances where if I'm doing a heuristic, like a function call or an assignment or something, I need to be able to walk up and down the tree sort of in a way that makes sense, right? And if you're trying to take that workflow and make it a generic sort of sequence of steps you would do over and over for different functions or different parameters or whatever, then adding on top of it, being able to walk up and down the tree, the more steps you have to take to get the information you want, it kind of blooms out of control. Because like in the case I have shown on this previous slide here, you know, there's nothing like a return value, and the decompilation is also very clean, right? So there's no references, there's no casts, there's kind of nothing around my set dialog item text a function that would make this an unusual case. But the more complicated your logic is, or if you're in an if statement or an assignment or anything like that, then as you walk up and down the tree, sort of the use cases kind of expand exponentially. And then the other piece of it is, you know, this is more or less hard coded to set dialog item text A and looking for a string argument. But if I want to change it to a different function name and say extract a number, then I have to rewrite all of this code essentially. You know, I can copy and paste it, and you know, it's only a couple line changes, but basically there's sort of a twofold problem of one, it's hard to convert this visitor prototype into something generic that you can use over and over when you're doing your analysis work. And two, you can even just see from the amount of times that I'm accessing I.x or I.a, and then there's an index, there's a bunch of kind of internal mechanics about IDA's underlying objects and representations that, you know, it's not that it's hard, it's just that it's a spin up process, and it takes a lot to kind of get your head around the first time. So what we've done is we've done all that work for you, and when you do this in FIDL, you get something like this. So we build a control flowinator for the same function. We have already gone through and sort of done everything that I've shown you in this visitor class on the right, and we've converted all of that into members in our control flowinator object, so I can extract all of the function calls with our c.calls mechanism, and then for each function call, you know, I can just go through and just check the name. And these are all sort of names and parameters that all make sense, or they all are easier to read, is the sort of end goal for us, right? And the idea being like, function called.name is a lot easier to extract than like calling a name API on a 3 reference deep sort of data member. So this is just a quick example, and Carlos is going to go into some more now about, we've sort of done the tedious mechanical parts for you, and we've integrated that all into our control flowinator function. So now when I want to write sort of a dynamic processing script, it's a lot easier to write code that's shown on the left than the code that's shown on the right, right? And then you have access to, like I said, a bunch of named tuples. We'll go through some more examples, and we have a bunch of essentially generic functionality. So, you know, anything that you would think of as like a semi-common problem you run into when scripting against a binary is something that we've already sort of wrangled the decompiler to expose to you in sort of an easy to use and easy to script against way.
So yeah, as Brian just said, one of the things that was important for us, it was of course like that this is easy to use, because if it's not easier to use than the raw API, then kind of defeats the purpose. So we try to, if you see the number of functions inside this, let's say, little API that we built on top of the raw API, there are like many functions. Some of them are like rather more or less, let's say, complex, but some of them are actually like a couple of line wrappers. But it's still, the idea is that if you see this wrapper in your code, it's going to have like a clear name. It's going to be wrapping something that you could do it, but then your code is going to be larger, it's going to be less clear, and it's going to be terribly tedious to do that all the time. So we try to, there's going to be like bazillions of functions in there. We're not going to go no way through those. They're pretty well documented. Let's say we put some work on that as well. So every time that we make a minor change or a large one, and we push the code, so documentation gets automatically generated from the code, and it gets pushed to read the docs. You're gonna get the links afterwards. So if you go to read the docs and search for any API, they have like kind of logical names, we think, and so everything's gonna be there, and you know that you always have the latest. So it's gonna be updated. This is what we're trying to say. So yeah. But we're going to show a couple of more or less contrived examples to give an idea of the things that you can do. They're not the most complex ones. You can really go down the rabbit hole in here. We try to strike a balance in between. Okay, look, this is rather powerful and easy, and so let's go for it. This is kind of a bit contrived. In this case, this C2 that you see in there is, of course, like a control flow inator objects. You're iterating through all the nodes in this graph. Remember that the thing at the end of the day is a graph. And then we have, for example, this API find elements of type. And what you have to do is imagine that you want to search for, I want an element, I want a node. I want to find a node that it has like a number inside it, you know, or it has whatever, like a reference or a pointer or whatever. And so you can do very easily this thing like in a loop. You say, okay, let's go through all the nodes inside this control flow inator. I want to find elements of this type, and the rest is just like a format, like a complicated format string. In this case, we're looking for numbers. And you see here the output, you have all those addresses and the number that is found in this, inside this node. So if you click whatever address like that one that's 67, it's going to take you to the line of decompiled code, and then you see indeed there is like an occurrence of a literal, so like a number, and this is in this case the 67. This is, as I said, like a very contrived example, only to kind of show you most of the things, most of the tedious things, most of the things that you're going to be using all the time, like, oh, I would like to search all the numbers that there is in this function. It's already in there for you. You know, clear APIs like find elements of type, this and that. And in this specific example, this is probably like an offset into a structure, so it's not very interesting. As I said, very contrived, but let's use exactly the same logic in a real case. So this is from one of our colleagues. It's a snippet, of course, from something that one of our colleagues uses in the wild. He was working in some malware that, of course, malware being as sneaky as it is, what it was doing is it had all the strings inside the binary encrypted. All those strings were decrypted in real time. This is this first line that you see in this strings variable. It's not really important how. This is just a specifics of this very specific malware. Just keep in mind that this strings is just an array to many strings that this malware is using, that when you're sitting on your disk is just garbage. Right now, we kind of emulated that the malware is running and decrypted all this stuff while it's running. And we have like an array of strings. This is another very, very useful API that you're going to be using all the time. So in this case, our colleague just realized that the malware is always using or referencing this array of strings that is now in memory decrypted. So what we're going to do is like search for all the calls inside the binary to this specific function. And then we're going to see, okay, for all those calls that you see, just give me the first argument. We're just checking that the first argument is indeed a number, this kind of a sanity check. And then we're saying, okay, now give me the real value of this number, in this case, you know, like whatever, 3, 4, 7. And this is being used as an index into this array. So this looks like very easy because it is very easy when you do it with FIDL. If you try to do the same thing, and again, we try to strike a balance. This is not like a terribly complicated example, but it's something like from real life, and that this thing happens like all the time in malware. So it is, almost 3-4 lines. The rest is just prints, or in this case, it's creating a comment, but it doesn't matter. It's like format string. If I throw you this snippet and you don't know anything about FIDL, you could have like a pretty educated guess like what is going on. That's we kind of strive that is something that it makes sense and it's logical, because it happens a lot that you write as whatever script and you go back then like 2 months afterwards and you're sitting there like, okay, what did I do? What is this thing doing? So yeah, this is kind of a real life example of something that is not exactly trivial, but it is way better. Well, the thing that we're trying to say all the time in this presentation is like life is better with FIDL. We may be biased, but we think so. So yeah, there's like, of course, like APIs for everything, and as well for interacting with the GUI in case you want to do some things that, printing lines or just putting colors on lines that match a specific criteria that you're looking for. So they're like many things. One of the APIs that we use all the time and would like to tell you about it is display all calls to. That, of course, you can imagine what it's doing. Imagine this case. It happens. This example is more from the vulnerability research part of things. Imagine that you are looking at the binary, and of course, you don't have symbols, so you all have those kind of function names, sub underscore something something, and life is less good than it could be. But by reversing, you realize, oh look, this function actually looks like it's doing some kind of logging. And in the arguments, it always, when it logs, it has the original function name of this specific function that is doing the call. And this may sound like very familiar to many of you because this happens a lot. So when you identify one of those that are doing some logging or printing error messages, it says like, okay, function original name, error in this and that, error code 127. So it's kind of, let's say, leaking this information that can be very juicy, because if you're able to harvest all those things and then rename those functions, then you get a lot more visibility and a lot more context on like what is going on while you are reversing. Again, we can all agree it's much better to have function names. So yeah, exactly. This is what we did. So there was all those references to that function, but of course, if you just go there and press X, you see that, but it's not helping much. But if you just do, as you can see here, simply display all calls to and the function name, you see all this. And this is very interesting to kind of, let's see, test your assumption that this is actually very quickly, that this is actually what you think it is. And in this case, for example, we can see the third argument. It appears that is, it's always like unique. So it appears that supports our thesis that this thing is leaking the original function names. So now you can, of course, like do something a bit more complex and just take this third argument, very easy with FIDL, and then you rename the function doing the call. That's very, very helpful.
Yeah, so just to kind of wrap up and put a little bow on this section, like I said, we've said it a couple times, but the big takeaway for us is that when you're confronted with sort of the problems that you normally run into that require scripting for, malware analysis or VR or whatever it happens to be, again, it's not that the existing tools are detrimental or deficient or anything like that, but our goal is to essentially extract away as much as possible worrying about the mechanics of how the actual decompiler works. So theoretically, right, if you think about it, what we've shown so far in terms of examples, that could almost be independent of any decompiler that you're using, right? Like we built it on top of IDA, and we built it on top of IDA sort of for very specific reasons. But the idea is, if I want to now write a script, so like some sample things that I've done with this is things like, oh, this is find all references to a string decoding function, extract the keys from the parameters. That can all be done with FIDL, and then you can just feed that into, you know, some kind of other tool like FlareEMU or something like that to actually do the string decryption. That's a pretty common one. Or because we have this control flowinator that's built on top of kind of logical statements seen in code, you can do things like if I want to track variable assignments or taint tracking, or I know this variable is a structure, so find all the structure members that are being referenced. The idea is we've built FIDL and the control flowinator to, as much as possible, extract away the mechanics of actually walking an AST. So there might still be cases where it's easier for you to get a call with FIDL and then start walking down the AST manually to extract some piece of information. But the idea is like those cases are kind of edge cases, and in the majority of situations you'd be able to just rely on the code that we've provided you and not have to worry about sort of, well, what kind of node is it? Oh, it's an addition node, so I need to do this logic, versus it's a subtraction node, versus it's a call or assignment. So we've kind of gotten rid of all of that. And basically we've exposed all that as generic functionality, right? So I mean, even what we showed originally of here's your control flowinator for a function, you could find all the function calls, locals, parameters, things like that. Even that could be used as the basis for your script too. So, you know, for us, the way we look at it, FIDL is sort of your generic functionality or your building blocks. And once you sort of extract away all the tedious mechanics of walking the AST yourself, now you can focus on like the heuristics that you care about, whether that is, you know, something to do malware analysis or something to clean up a binary or something to track object or whatever it happens to be. The idea is we've carved off a big chunk of the work that you would normally have to do in order to wrangle the decompiler to give you the information that you want. And now rather than worrying about that or worrying about, you know, like I said, edge cases of what different ASTs for different functions can look like, you can just focus on the stuff that you care about, whatever higher level heuristics you're trying to develop, and, you know, more or less the fun stuff, right? So that's our ideas. That's sort of the design philosophy behind FIDL and the problems we're trying to solve. For more complete examples, like Carlos said, we are striving to update this where we can and as much as possible and provide sort of useful examples to the community. But you know, along with that, we also have API documentation. So all of the functions that Carlos said we didn't have time to go over for this presentation, they're all kind of listed here. So you can see, you know, how much we've exposed to you by default. And like I said, the idea is hopefully you can use that as kind of your foundational building block to whatever script you happen to be working on.
Okay, cool. So we hope that right now you're thinking, okay, I like this FIDL, this is a very cool thing. I like to check it out. But yeah, and it is. We still think so. We may be biased. But still, we have been talking about working on one binary. It must be a huge binary. Maybe have like 2,500 functions. So it's much better now. And FIDL helps a lot with that. But still, we're talking about one binary. And most of the time, either we're doing like, I don't know, malware reversing, or especially if we're doing like vulnerability research and we have a very large code bases with, you know, hundreds of DLLs or thousands, we're looking at large systems. We would like to do this thing at scale, you know. So we're going to talk briefly about how we do it. So right now, this was initially our workflow. You know, you open IDA, you load the binary, you execute a FIDL script, you close IDA, and then you repeat. So then we realized this is kind of a limitation. This is not the way to go. No, this is not how life should look like. No, thanks, but no. So we kind of thought about it, and we wrote something that we internally named the Citadel. And this has like a web interface and drag and drop and distributed processing. It executes either headless, and it's Docker prepare. So yeah, this is progress. This is 2020. This is exactly how life, reversing life, should look like. So yeah, let me show you like very quickly a tale from the Citadel. Yes, we are Rick and Morty fans, of course. Who isn't? So essentially it looks like this. And I know after the previous introduction, yeah, it's kind of turned off. It's just another web interface and another distributed processing system. So it looks like this. Here you have your campaigns. We call it campaigns. Campaigns is essentially like a bunch of binaries that you throw in there and some analysis that you want to run on them. And yeah, essentially what you do is you go here, you go to upload campaign, then you filter some data about this campaign. You drag and drop a bazillion of files in there. It's all very web 2.0. Then you go to your analysis workflow. Then you have some predefined analysis, or you user-defined ones. You kind of drag and drop this thing to the right. You can reorder this thing and say, okay, those are the analyses that I want you to run in this specific order. And you know, it's all like very flashy. And well, then you create your campaign, and then you have it. For example, then it appears into your campaigns, and it's ready to go. What you do now is you fire up some workers that are essentially, so in a nutshell, they're like running either headless, pulling up your files, your input files, opening in either, and executing those scripts, sending back and forth their results. It's all very JSON-y. And then, you know, it's essentially that. At the end, if you're lucky, this is like a very simple example, of course, you get like many results. You can go in here and see, oh, okay, this looks like interesting. This is just like a very brief, just to catch your eye. This is like a very simple example. We just calculated the complexity of those functions just for the sake of this example. But you can put there like real, more or less refined heuristics if you're looking for some kind of bugs that, you know, usually look like this. You say, when you see anything in whatever function, in whatever binary that looks like this, please tell me, because what I want to do is you go here, you click in there, you download the IDB, and all the information that is displayed in here is marked inside the IDB. So, you know, you can use Control M, and you have a list of them. You just go directly to the point in the disassembly where there may be something that is sketchy that you would like to take a look as a human right now, you know, with a human brain. Yeah, and essentially that's it. And this is where we were promising you all the time, you know, we're gonna get it. Those are the links. You're gonna get the presentation. It's essentially just going to github.com, FireEye. This is where we work, and FIDL. There is the documentation as well that is automatically updated. I cannot stress enough, this is actually a cool thing. And we just want to let you go with this thought that the compilation, we think it is the future. And you see, I was watching like a Star Trek Discovery, and I was like, is this actually hex race? It is hex race. So, you know, in 200 years, 400 years, apparently the compilation is going to be still a thing, as well as, unfortunately, the Win32 API. So with that, time for questions.
Thank you so much, Carlos and Ryan. Let's give them a round of virtual applause. Carlos is waiting in the Discord channel for any questions if you have, so please feel free to post your questions there. And that's it for day one, folks. It's a wrap. We made it dispute the earlier technical hiccups. Thank you so much for bearing with us, and see you guys tomorrow for day 2 stock. Well, for track 1. Track 2 is still going on. In the meantime, the car hacking CTF by Car Security Quarter and Zenith Lab crypto challenges are still going on until the end of tomorrow. Be sure to try out those challenges if you still don't have enough HITB goodness for today. See you on our Discord channel, and see you back here tomorrow. Over and out. Thank you for tuning in.